Chaos theory. Prologue. Chaos begins before meaning. The silence. Before any law. Before the first star tore itself into existence. Before hydrogen chose to bind to itself. Before gravity even knew it was gravity. The universe was not order, and it was not disorder. It was not structured, and not poetic. It simply was. Total silence. Total potential. And that is where our story will begin. Not in the triumph of mathematics, not in the comfort of equations, not in the philosophical metaphors that humans invented to feel less alone, but in the terrifying space before meaning. Because meaning is a human invention, chaos is not. For billions of years, the universe did not care what truth was. It simply expanded, exploded, cooled, ignited again. Stars formed, died, collapsed into black holes, and their death clouds seeded new solar systems, including ours. We imagine laws. We imagine structure. But structure is not primal. Chaos is primal. And this is the most important psychological starting point for this story. We must wipe the board clean. We must return to zero. We must temporarily forget the security blanket of explanations. Because explanations are late inventions. Only then can we see the universe as it actually is. We were born in chaotic dust. Humanity often imagines that civilization began with logic, writing, geometry, calendars, astronomy. But those were just tools carved from fear. Before those, there were storms, lightning, volcanoes, seasons, comets, all terrifying expressions of a cosmos beyond control. We were not born into a rational universe. We were born into a violent and unpredictable universe, and then we desperately tried to rationalize it afterward. This is why every ancient civilization had cosmology, because the universe was overwhelming. Mesopotamia, Egypt, India, China, Maya, all face the same trauma. The sky is not stable. The stars move. The seasons shift. The river overflows. The rainfall disappears. The lightning strikes at random. The world does not repeat patterns perfectly. It only pretends to. So humans needed narrative, not because narrative was true, but because chaos was emotionally unbearable. We invented gods to survive complexity, not to understand it. Modern science is still a response to fear. We flatter ourselves with the idea that modern physics replaced mythology. No, it simply rebranded it. Our equations are just newer, more precise forms of the same ancient prayer. Please let the world be predictable. Laplace dreamed of total determinism, a universe where every atom could be computed perfectly. Newton imagined heavenly bodies as clockwork, elegant gears in a cosmic machine. And then the three-body problem arrived, and like a blade, it cut through the fantasy. Three simple bodies, three gravitational masses, and suddenly the equations fall apart. Not because they are complicated, but because beyond certain thresholds, their future is literally uncomputable. It is not a puzzle we haven't solved yet. It is a puzzle that cannot be solved. Not even in theory, because the universe is not structured like a machine. It is structured like turbulence. Modern science has been trying to digest this trauma for over a century, and it still hasn't swallowed it. Chaos is not randomness. It is sensitive dependence. The cliché phrase, butterfly effect, is not just poetic exaggeration. It is the most humiliating sentence physics ever produced, because it means we cannot compute reality to arbitrary precision, even in principle. Not because our instruments are weak, because reality itself amplifies microscopic uncertainty. Chaos is not noise. Chaos is not disorder. Chaos is extreme sensitivity, and sensitivity is the enemy of determinism. Meaning is a human reflex after impact. So here is the uncomfortable truth. The universe does not produce meaning. Humans do. Meaning is a reaction, not a property of the cosmos. We look at chaos, and we write poetry. We look at chaos, and we build equations. We look at chaos, and we invent gods. Meaning is not woven into space. Meaning is a bandage placed on confusion. This is why modern people still feel existential disorientation when confronted with chaos theory. It is not just a scientific discovery. It is a threat to identity. We need the world to be stable. We need the world to be intelligible. We need to believe we are not living inside uncontrollable turbulence. But we are. Our species is a temporary computation. We think we are the center of narrative. But we are a short-lived emergent pattern inside the turbulent evolution of stars. This is the perspective shift intro demands. We are not the authors of the universe. We are a downstream artifact of chaos. Our brains are not truth machines. They are survival machines. We do not seek truth. We seek orientation. And sometimes, orientation is a lie. This series will be a descent, not a comfort. Most science stories comfort the viewer. We will not. We will do the opposite. We will peel away the narrative security layer by layer, from classical mechanics to Poincaré, from determinism to chaotic uncomputability, from the arrogance of control to the humility of existing inside a universe whose future cannot be compressed into formulas. This is not just information. It is disillusionment. It is psychological dismantling. Because at the bottom of all scientific progress, the foundation is not confidence. The foundation is, we do not know. The Beginnings is a fall into truth. The first episode of this series is not an argument. It is an exile. We exile the viewer from certainty. We exile the viewer from comfort. We exile the viewer from the childish myth of total computability. Only when the mind is finally thrown out of the kingdom of false order can we even begin to speak of what chaos theory actually is. The universe was born in chaos. Reality is still unfolding in chaos. And meaning, the meaning we so carefully manufacture, is only our fragile response to this violent inheritance. This is where our journey begins, in the terrifying beauty of the unexplainable, in the silence before narrative, in the chaos before meaning. And now, let us fall. If this descent into the abyss of reality, stripped of comfort, resonates with you, then I invite you to join this ritual of clarity, subscribe to the Hidden Framework, turn on notifications, and support this journey so that we can continue to expose the unfiltered structure of existence, not the comforting myth, but the truth as it actually is. Episode 1. The Butterfly Effect. The smallest decision that rewrites the cosmos. They say the fluttering of a butterfly's wings in Brazil can set off a tornado in Texas. I heard those words for the first time at a cocktail party in Manhattan, spoken by a hedge fund manager who was explaining why his algorithms failed during the last market crash. The phrase hung in the air between us, suspended in the golden light of a penthouse overlooking Central Park. It seemed poetic, almost mystical, a perfect blend of chaos and poetry to explain away millions in losses. What he was referencing, of course, was chaos theory, though like most who invoke it at parties, he understood just enough to be dangerous. The real story begins in the winter of 1961, in a small, overheated room at MIT. Picture yourself as Edward Lorenz, a meteorologist with thinning hair and thick glasses, hunched over a Royal McBee L GP30 computer. The machine occupies most of the room, humming with the weight of its vacuum tubes and transistors. You've been running weather simulations for months, feeding the computer differential equations that model atmospheric conditions. Today, you're in a hurry. Instead of typing in the full six-decimal number from your previous run, 0.506127, you round it to 0.506. A tiny difference, less than 1 part in 1,000. The simulation should be nearly identical. You wait as the computer churns through calculations, printing results on sheets of paper that pile up beside you. At first, the numbers track closely with your previous run, but as you scan down the columns, something impossible happens. The predicted patterns diverge, slightly at first, then dramatically. By the equivalent of 2 simulated weeks, the rounded number produces an entirely different weather system. Clear skies where storms should rage, cold fronts where there should be warmth. This cannot be. The equations are deterministic. The laws are fixed. You changed almost nothing, and yet the future they predict has fractured into something unrecognizable. Lorenz wasn't witnessing a computer error. He was discovering what would eventually be called the butterfly effect, the haunting reality that in certain systems, microscopic changes in initial conditions can cascade into macroscopic differences in outcomes. A revelation that would challenge our deepest intuitions about cause and effect, about order and disorder, about our ability to predict the world around us. The golden chambers of Wall Street and the pristine laboratories of meteorology seem worlds apart. Yet both confront the same unsettling truth. Some systems, despite following rigid mathematical rules, remain fundamentally unpredictable over time. This is the core insight of chaos theory, an idea that has spread from physics to biology, from economics to ecology, from computer science to philosophy. But what exactly is chaos theory? The term itself is misleading. In common language, chaos suggests randomness, disorder, a complete absence of rules. The scientific meaning is quite different and far more unsettling. Chaos, in mathematical terms, describes systems that are deterministic, governed by precise equations, but exhibit sensitivity to initial conditions so extreme that long-term prediction becomes impossible in practice. Think of a perfect pool shot. The cue strikes the ball at a precise angle with exact force. Physics dictates exactly where each ball will travel, but introduce the tiniest imperfection, a microscopic divot in the felt, an imperceptible tremor in the player's hand, and by the third or fourth collision, the outcome might be entirely different. The system isn't random. It's following ironclad physical laws. Yet knowing those laws doesn't grant you predictive power beyond a certain horizon. This distinction, determinism without predictability, is what makes chaos theory so profound and so disturbing. The universe may well be clockwork, but it's clockwork so sensitive that no observer could ever gather enough information to forecast its behavior beyond short timescales. The significance of this insight extends far beyond weather forecasting or billiards. It challenges a worldview that has dominated Western thought since the Enlightenment. The notion that with enough knowledge and computational power, everything becomes predictable. Pierre-Simon Laplace, the 18th century French mathematician, famously imagined a vast intelligence that, knowing the position and momentum of every particle in the universe, could see all of history, past and future, in a single mathematical gaze. Chaos theory doesn't disprove Laplace's dream in principle, but it renders it forever unattainable in practice. No real intelligence, no matter how vast, could gather initial conditions with infinite precision. And without infinite precision, predictions of chaotic systems decay into uselessness. This humbling of scientific ambition has rippled through virtually every field of human inquiry. Biologists studying population dynamics discover that simple predator-prey models produce wildly unpredictable outcomes. Economists realized that markets might be inherently unpredictable beyond short timescales, not because they lack governing laws, but because those laws amplify tiny fluctuations into major shifts. Medical researchers found chaotic patterns in heart rhythms and neural activity, suggesting that some disorders might arise not from broken mechanisms, but from hypersensitive ones. The cultural impact has been equally profound. The butterfly effect has become shorthand for interconnectedness and unintended consequences. Fractal patterns, the visual signature of many chaotic systems, where the same structures repeat at different scales, have influenced art, architecture, and design. The phrase "everything is connected" has evolved from mystical intuition to mathematical reality, though often misunderstood and over-applied. Chaos theory has also been misused and misappropriated. It's been invoked to justify everything from market deregulation, systems are too complex to control, to spiritual doctrines, science now proves ancient wisdom. It's been stretched beyond recognition in self-help books and management seminars. And it's been weaponized to cast doubt on legitimate scientific predictions, most notably in climate science, where critics misuse chaos theory to suggest that long-term climate models must be unreliable. These misapplications highlight why understanding chaos theory properly matters. This isn't merely academic pedantry. It's about grasping one of the most profound scientific insights of the 20th century, one that reshapes our relationship with prediction, control, and uncertainty. In the pages that follow, we'll explore this fascinating landscape in depth. We'll examine the core mathematical ideas that define chaos, trace the historical development from Poincaré's early insights through the computational revolution that made chaos visible, and meet the interdisciplinary community of scientists who pushed against established paradigms. We'll weigh the evidence, separating systems where chaos has been rigorously demonstrated from those where it remains speculative. We'll see how different disciplines, from physics to philosophy, have interpreted and applied these ideas. And we'll analyze how chaos theory has been represented in popular culture and online discourse, often with more enthusiasm than accuracy. Throughout, we'll maintain a critical perspective. Chaos theory is neither a universal key that unlocks all complexity, nor a mere mathematical curiosity. It's a powerful framework with specific domains of applicability and important limitations. Understanding both its power and its boundaries is essential for anyone seeking to navigate an increasingly complex world. As Lorenz himself wrote in his later years, chaos, when the present determines the future, but the approximate present does not approximately determine the future. This elegant formulation captures both the precision and the profound implications of the theory. It tells us that the universe may well be clockwork, but our ability to read its movements will always be imperfect, always limited by our finite capacity to measure and calculate. For some, this realization is deeply unsettling. a mathematical proof that uncertainty is not merely a product of our ignorance, but woven into the fabric of reality. For others, it's liberating. A recognition that emergence, novelty, and surprise are inevitable features of even the most rigidly determined systems. As we drift off to sleep tonight, contemplating these profound tensions between order and unpredictability, perhaps we might find a certain comfort in the butterfly's wings, in the knowledge that even in a universe governed by mathematical law, the future remains perpetually open, perpetually surprising, perpetually beyond our grasp. A soft amber glow bathes the library as night descends outside floor-to-ceiling windows. Rain traces delicate rivulets down the glass, creating shifting patterns that seem both random and ordered. Within this sanctum of old wealth, leather-bound volumes line mahogany shelves that reach toward an arched ceiling. The room's sole occupant, Elias Whittington III, traces his finger along equations in an open mathematics journal, his reflection fragmenting in the crystal tumbler of scotch beside him. Chaos, he whispers, is perhaps the most misunderstood concept in modern science. Elias rises, moving toward a peculiar apparatus on a marble pedestal near the window. Two brass pendulums, one suspended from the other. With a surgeon's precision, he pulls the lower pendulum slightly to one side and releases it. The contraption begins to move, at first with a predictable swing, then tracing increasingly complex patterns that seem to defy intuition. "It's not randomness," he continues, speaking as if to an unseen audience. "A chaotic system is perfectly deterministic. If you know the starting point with infinite precision, the future is fixed. But infinite precision is impossible, and that's the trap." The double pendulum swings in looping, unpredictable arcs, the light catching the brass and sending golden reflections dancing across leather and wood. Elias watches, transfixed. This simple mechanical system, no dice, no randomness, just two rods, two joints, and Newton's laws. Yet if released from 1/1,000,000th of a degree different, it would trace an entirely different path. "That's sensitivity to initial conditions," he murmurs, his voice blending with the patter of rain and the occasional creak of century-old timber. Tiny differences explode. Thunder rolls in the distance as Elias returns to his desk, where complex equations sprawl across pages of expensive stationery. His fountain pen scratches softly as he adds notation in the margins. The family fortune that allows this meditative existence was built on shipping, predicting weather patterns across oceans. Ironic, he thinks, that his obsession would become the very thing that makes such prediction fundamentally limited. "Weather," he says to the empty room, "is perhaps the perfect example. Perfectly deterministic physics, governed by equations we've understood for over a century. Yet forecasts become essentially meaningless beyond about 2 weeks." He pauses, taking a sip of scotch, savoring the complex interplay of flavors that, like the systems he studies, arise from simple ingredients interacting in nonlinear ways. "Nonlinearity," he continues, "the second hallmark of chaos. Small causes don't guarantee small effects." He gestures toward the rain-streaked window. A butterfly flaps its wings in Brazil, and weeks later, perhaps a tornado forms in Texas that otherwise wouldn't have, or doesn't form that otherwise would have. The math allows either possibility. The pendulum continues its dance, never quite repeating, yet never escaping an invisible boundary. Elias walks toward it again, mesmerized by the way it traces what mathematicians call a strange attractor, a shape in phase space that reveals structure within apparent disorder. Strange attractors, he whispers. The system never repeats, but it's not random. It's bounded, structured, fractal. From a nearby shelf, Elias retrieves a leather portfolio. Inside are correspondence letters from colleagues at universities worldwide. Mathematicians, physicists, biologists, all part of an emerging community studying what some call nonlinear dynamics, others deterministic chaos, and still others complexity theory. Some call it nonlinear dynamics, or deterministic chaos, or complexity, he says, fingering the embossed letterhead of the Santa Fe Institute. The name matters less than the realization. There are systems where knowing the rules doesn't mean you can see the future. The wealth that surrounds him, the rare first editions, the antique furnishings, the estate beyond these walls, all came from ancestors who believed the world was fundamentally predictable. Plan carefully enough, they thought, execute precisely enough, and fortunes could be built on certainty. Yet here he stands, their heir, having dedicated his life to understanding the mathematics proving them wrong. He picks up a letter from a mathematician colleague studying iterated maps. We discovered that even simple equations can have behavior so complex it looks like noise, the letter reads. Elias nods in recognition. This is no mysticism, no New Age philosophy. It's a branch of mathematics and physics with rigorous foundations, despite its sometimes poetic implications. The grandfather clock in the corner chimes midnight. Elias moves to his desk and opens a leather-bound journal filled with his own notes. His work bridges disciplines, pure mathematics of dynamical systems, applications in meteorology, even tentative explorations into economics and biology. Chaos theory emerged as a cohesive field relatively recently, he writes, the ink flowing smoothly across the page, with roots stretching back to Henri Poincaré in the late 19th century, but only crystallizing between the 1960s and 1980s. He pauses, considering Edward Lorenz's accidental discovery in 1961, how a meteorologist running computer simulations rounded numbers in a printout, fed them back in, and found wildly divergent results from such minor differences. Technology finally allowed what theory had hinted at decades earlier. The rain intensifies, a curtain of water now cascading down the windows. The sound creates a cocoon around the library, insulating Elias in this moment of reflection. He thinks about the temporal scope of this discipline that has consumed him, how chaos theory remained obscure for decades before exploding into scientific consciousness, now integrating into mainstream science across countless fields. The integration continues today, he murmurs, from weather prediction and turbulence modeling to heart rhythm analysis and population dynamics. Elias returns to the double pendulum, which has nearly settled into stillness. With the gentlest touch, he sets it in motion again, this time from a slightly different initial position. The pattern that emerges bears no resemblance to its previous dance, despite starting from an almost identical state. We are witnessing the mathematics of unpredictability, he says. Not the absence of causation, but the presence of extreme sensitivity. He moves to a leather Chesterfield sofa, sinking into its embrace as he contemplates the implications. The fortune that allows him this luxury of contemplation was built on the illusion of control, yet he finds deeper meaning in understanding the limits of prediction. Perhaps true wisdom comes not from trying to predict the unpredictable, but from developing robust strategies that acknowledge fundamental uncertainty. The double pendulum continues its erratic ballet, tracing out the signature of chaos in the amber light. Elias watches it with the reverence others might reserve for religious icons. In these simple brass rods, he sees the universe's truth, deterministic yet unpredictable, ordered yet chaotic, simple in rules yet infinite in expression. Chaos theory, he reflects, sits at an unusual intersection, a mathematical framework, an applied science, and a philosophical touchstone. He thinks of the cultural impact, how this scientific framework has spilled beyond academia into popular understanding, often misinterpreted along the way. The metaphor of the butterfly effect has captured public imagination, though frequently divorced from its mathematical foundations. The clock ticks steadily as Elias makes notes in his journal. Outside, the storm continues unabated. Each raindrop's path down the window a miniature chaotic system, sensitive to microscopic variations in the glass surface. Now that we know what chaos is, Elias writes, his penmanship flawless despite the late hour, the question becomes, what exactly does it claim about the world? What are the core scientific assertions, and how universal are they? He closes the journal, leaving that question for another night. Rising, he approaches the window, watching lightning illuminate the estate grounds. The landscape transforms momentarily into a tableau of silver and shadow before returning to darkness. In that flash, Elias sees the perfect metaphor for chaos theory itself. Brief illumination revealing patterns otherwise hidden, yet leaving many mysteries intact. The double pendulum has nearly come to rest again. Elias makes no move to restart it. Instead, he drains the last of his scotch, the warm glow spreading through him as he contemplates a universe governed by equations, yet resistant to perfect prediction. There is comfort in this understanding, a certain freedom in accepting the limits of foreknowledge. Deterministic, he whispers, but not predetermined, at least not in any way we can calculate. Elias switches off the amber lamp, leaving only moonlight filtered through rain-streaked glass. The library settles into silence, broken only by the pendulum's diminishing movement and the steady rhythm of the storm. In this moment, chaos and order seem not opposites, but companions, two faces of the same mathematical reality. And in this understanding, Elias finds both intellectual satisfaction and a curious peace. The wealth of knowledge, perhaps the greatest fortune of all. Charles Worthington rested his hand on the deep mahogany desk, allowing his fingertips to trace the polished grain as he stared through the floor-to-ceiling windows of his Manhattan penthouse office. 67 floors below, the city pulsed with evening traffic, thousands of individual decisions creating patterns visible only from his elevated perch. "Tell me again," he said quietly to Professor Elena Reeves, who sat across from him, "about these core claims of chaos theory, in simple terms." The professor's reflection appeared in the glass beside his own. She'd arrived 20 minutes ago at his request. The hedge fund billionaire's curiosity about mathematical modeling had evolved into something of an obsession lately. "There are 5 fundamental assertions," she replied, adjusting her wire-framed glasses. "First, deterministic systems can be practically unpredictable. This means a system can follow absolute mathematical rules, yet remain impossible to forecast with any precision beyond a certain time frame. Charles turned, his expression thoughtful. Like Lorenz's weather equations. Precisely, though completely deterministic, meaning no randomness whatsoever. His three simple equations produce behavior so complex that long-term prediction became impossible. The city lights flickered beyond the glass, a constellation of human activity. Charles walked to a side table, where a pendulum installation sat. 3 chrome arms suspended from fine wires, each ending in a polished silver sphere. He set them in motion with a gentle touch. The butterfly effect, Elena continued, watching the pendulums begin their dance. Small causes can create enormous effects. An infinitesimal difference in initial conditions cascades into vastly different outcomes. Edward Lorenz discovered this accidentally when he rounded a variable from 6 decimal places to 3, and his simulation produced an entirely different weather pattern. The pendulums swayed hypnotically, their paths growing increasingly complex as they influenced each other. The third claim involves strange attractors and fractal structure, Elena said. Complex systems don't wander aimlessly. They follow patterns with infinite detail. Charles nodded toward a large framed print on his wall. A computer-generated visualization of the Lorenz attractor, resembling a butterfly's wings rendered in thousands of blue lines. The system never repeats itself precisely, he murmured, yet always remains within that shape. Yes, every trajectory is unique, never crossing itself, yet always orbiting within that butterfly-like structure. And if you magnify any section, you find similar patterns repeating at smaller scales, the hallmark of fractal geometry. A housekeeping robot quietly entered, refreshed their waters, and departed with mechanical grace. Charles returned to his desk and activated a holographic display embedded in its surface. Order within apparent randomness, he said, as the display showed a chaotic stock market graph. The fourth claim. Elena leaned forward. Indeed. Take the Feigenbaum constants, precise mathematical values that govern how systems transition from order to chaos. They're universal, appearing in diverse phenomena, from dripping faucets to animal populations. These constants reveal hidden order within seemingly random behavior. The hologram shifted to display multiple systems side by side, a heartbeat monitor, population cycles of predator and prey, fluid turbulence patterns. Which leads us to the fifth claim, Elena continued. Universality, the same patterns appearing across completely different systems. The mathematics of chaos isn't just applicable to weather or mechanical systems. It appears in biology, economics, even social dynamics. Charles nodded slowly, which explains why my quantitative analysts find similar structures in financial markets, though they argue constantly about how to interpret them. That brings us to an important point, Elena said. Chaos theory isn't monolithic. There are distinct camps with different approaches. She rose and walked to his whiteboard wall, picking up a marker with practiced ease. First, the mathematical purists. They insist on rigor, theorems, invariance. They're concerned with proving properties of specific equations and mapping the abstract landscape of dynamical systems. To them, chaos theory is a branch of mathematics. Charles smiled faintly. I've met some of them. Brilliant, if somewhat disconnected from practical applications. Then there are the applied scientists, Elena continued, writing on the board. They build models of real systems, climate patterns, cardiac arrhythmias, population dynamics. They're less concerned with mathematical purity than with making chaos theory useful for prediction and control. The marker squeaked as she wrote complexity scientists and popular interpreters. The complexity and network scientists have moved beyond low-dimensional chaos to study high-dimensional systems with many interacting parts. Ecosystems, economies, neural networks. They focus on emergence and self-organization rather than classical chaos. Charles's eyes narrowed. And the popular interpreters? Elena capped the marker, her expression carefully neutral. They extend chaos theory into metaphors about personal destiny, organizational management, even spirituality. They've written bestsellers applying butterfly effects to everything from career choices to romantic relationships. I sense your skepticism. The mathematicians are rigorous but cautious in their claims. The popularizers are bold but often wrong. The tension between these approaches is significant. Charles walked to the bar and poured himself a small measure of Macallan 25. My chief investment officer subscribes to chaos-based trading theories, claims markets follow strange attractors. Is he a scientist or a popularizer? Elena accepted the scotch he offered, swirling the amber liquid. That depends on his mathematical rigor and empirical testing. Markets certainly exhibit nonlinearity and sensitivity to initial conditions, but proving true mathematical chaos is challenging. Let me ask you something else, Charles said, returning to his desk. These routes to chaos you mentioned in your paper, period doubling cascades and such, explain those. Elena sipped her drink. Systems often transition from order to chaos through specific pathways. The period doubling cascade is the most famous. A system that oscillates steadily begins to oscillate with twice the period, then 4 times, 8 times, and so on, until the behavior becomes chaotic. Mitchell Feigenbaum discovered this follows a universal pattern. And the other routes? Quasi-periodicity and torus breakdown, when multiple oscillations interact and eventually destabilize. Intermittency scenarios, where a system alternates between predictable and chaotic behavior. Crises, where attractors suddenly change or collide. Each represents a different road to unpredictability. Charles activated his desk display again. You've mentioned several technical terms. I'd like to understand them better. Of course. Let's start with nonlinearity, feedback, and saturation. These create the conditions for chaos. In linear systems, effects are proportional to causes. In nonlinear systems, they aren't. And that's where chaos can emerge. The display showed a diagram of a simple feedback loop. Feedback occurs when a system's output influences its future state, Elena explained. Positive feedback amplifies changes. Negative feedback dampens them. Saturation is when a system hits natural limits, like a population that can't grow beyond its environment's capacity. Charles nodded thoughtfully. And attractors? Think of them as the destinies of dynamical systems. A fixed point is a single stable state, like a pendulum coming to rest. A limit cycle is a repeating pattern, like a heartbeat. A strange attractor is chaotic, never repeating, yet confined to a specific region of possibility space. The billionaire's eyes reflected the blue light of the display. Lyapunov exponents? They measure sensitivity to initial conditions, how quickly nearby trajectories diverge. Positive Lyapunov exponents indicate chaos. In such systems, prediction accuracy decays exponentially with time. Outside, rain began to patter against the windows, distorting the city lights. Bifurcations are transition points, Elena continued, where small parameter changes cause sudden qualitative shifts in behavior, like water changing from steady flow to turbulence as velocity increases. The rain intensified, creating fractal-like rivulets down the glass. Speaking of fractals, she said, they're self-similar structures that look similar at different scales, like coastlines that remain jagged, whether viewed from a satellite or standing on the shore. Strange attractors often have fractal dimension, not whole numbers like 1, 2, or 3, but fractions like 1.26. Charles finished his scotch. And these last terms, embedding dimension, Poincare section, invariant manifolds, technical tools for analyzing chaotic systems. Embedding dimension refers to how many variables you need to fully capture a system's behavior. A Poincare section is a slice through a system's trajectory that simplifies analysis. Invariant manifolds are structures within state space that help organize chaotic behavior. The rain had stopped as suddenly as it had begun. Charles stood and walked to the window again, looking at the glistening city. When I was building my first quantitative trading model, he said quietly, I discovered something unsettling. I could predict short-term market movements with reasonable accuracy, but beyond a certain horizon, precision collapsed completely. I'd found the prediction horizon, the chaos barrier. Elena joined him at the window. That's the fundamental insight. Some systems, despite being completely deterministic, resist long-term prediction, not because of our ignorance or insufficient data, but because of their intrinsic mathematical nature. It changed how I see the world, Charles admitted, not as random, but as determined yet unpredictable. There's a difference. They stood in contemplative silence, watching the city below. Millions of individual decisions flowing like currents in a vast social fluid, creating patterns visible only from above. The emergent order of apparent chaos. We found universal numbers, Elena said finally. The same constants appearing in dripping faucets, electronic circuits, and population models. That's when we knew chaos wasn't just a curiosity. It's a fundamental property of complex systems. Charles turned to face her. If these claims are real, how were they discovered? What took so long? Newtonian physics is centuries old, yet chaos theory only emerged in my lifetime. Elena smiled. That, she said, is a story of technological barriers, scientific resistance, and a few remarkable insights that changed everything. The billionaire returned to his desk and pressed a button. Ms. Reynolds, please reschedule tomorrow's meetings. The professor and I have more to discuss. In the darkened office, the holographic display continued to trace the outlines of strange attractors, mathematical shapes defining the boundaries of the unpredictable, the ordered patterns hidden within apparent randomness. The year was 1890, and Henri Poincaré found himself besieged by a problem that had haunted the finest minds in Europe for 2 centuries. In his study overlooking the Seine, surrounded by stacks of calculations, the French mathematician stared at his work with growing unease. He had discovered something disturbing in his analysis of the 3-body problem. The seemingly simple question of how 3 celestial bodies move under mutual gravitational attraction. What Poincaré glimpsed that autumn night would ultimately reshape our understanding of the universe. though the world would not recognize it for nearly 80 years. "I see an impossibility," he whispered to himself. "Not because we lack knowledge, but because the system itself forbids prediction." His quills scratched furiously across parchment as he documented what he called homoclinic tangles, trajectories that would cross and recross themselves in patterns of infinite complexity. Even the slightest difference in starting position would eventually lead to wildly divergent outcomes. The predictable clockwork universe of Newton was dissolving before his eyes. Poincaré published his findings, but few could grasp their significance. Without tools to visualize these infinitely complex tangles, his revolutionary insight remained buried in dense mathematical language, a seed planted in soil not yet ready to nurture it. The mansion was silent, save for the gentle ticking of the grandfather clock, marking time's relentless march. Poincaré's discovery would lie dormant for decades, waiting for technology to catch up to his vision. In the interim, others brushed against the edges of chaos. In the 1920s, Balthasar van der Pol studied electrical circuits whose oscillations refused to behave according to linear expectations. The vacuum tube circuits would produce rhythms that seemed almost alive, regular, then irregular, defying simple mathematics. Meanwhile, Ludwig Boltzmann's statistical mechanics began exploring how order emerges from disorder at the molecular level, while later mathematicians like Andrei Kolmogorov developed ergodic theory to describe systems evolving through all possible states. But these were fragmentary insights, pieces of a puzzle no one realized they were assembling. The true rebirth would come in a modest office at MIT in 1961. Edward Lorenz, meteorologist and mathematician, was running weather simulations on an LGP-30 computer, a primitive machine by today's standards, slower than a modern calculator. The room hummed with the mechanical breathing of this early computer as it processed Lorenz's 12 equations modeling atmospheric convection. One winter afternoon, Lorenz wanted to extend a simulation he had run earlier. To save time, he started midway through, manually inputting numbers from the previous printout. The machine whirred to life, calculating the artificial weather patterns. But as Lorenz returned from fetching coffee, he noticed something strange. The new weather patterns were diverging dramatically from the original run. Puzzled, he checked his inputs. He had entered 0.506 instead of the full value of 0.506127. The difference was microscopic, less than 1 part in 1,000. "That's impossible," he murmured, watching the patterns on his printout. The system should produce nearly identical results with such similar starting conditions. But it didn't. The tiny discrepancy grew exponentially until, within the equivalent of a few simulated weeks, the weather predictions were entirely different. Lorenz had rediscovered what Poincaré had glimpsed decades earlier. In nonlinear systems, infinitesimal differences in initial conditions could lead to vastly different outcomes. The butterfly effect was born, though Lorenz wouldn't use that term until years later. What made Lorenz's discovery different from Poincaré's was visualization. The LGP-30 allowed him to see the patterns emerging. When plotted in 3 dimensions, his system traced a strange figure. 2 lobes connected in a complex dance, never repeating, never intersecting, yet always remaining within a bounded region. This was the first glimpse of what would later be called the Lorentz attractor, a shape as haunting as it was beautiful. Long-range weather forecasting, Lorentz concluded in his 1963 paper, is impossible in principle. The scientific establishment greeted this heresy with silence. The paper languished in the Journal of Atmospheric Sciences, largely unread by mathematicians who might have appreciated its significance. Meanwhile, across the Atlantic, two European scientists, David Ruel and Floris Takens, were puzzling over turbulence in fluid dynamics. In 1971, they proposed that turbulent flow could be understood as a strange attractor, a term they coined to describe the weird geometries that emerged from their equations. Without knowing it, they were building bridges to Lorentz's weather model. The 1970s saw the disparate threads begin to weave together. James York, an American mathematician, published a paper with the audacious title, Period 3 Implies Chaos, in 1975. For the first time, the word chaos entered the scientific lexicon as a technical term rather than a synonym for disorder. York and his co-author, Tianyin Li, had discovered that certain simple mathematical rules could produce astonishingly complex behaviors. We decided to call it chaos, York later explained, because that's what it looked like, even though we knew there were hidden patterns within the apparent randomness. The mathematical foundation deepened when Mitchell Feigenbaum, working late nights at Los Alamos National Laboratory with a programmable calculator, discovered something remarkable. The way that systems transition from order to chaos follows universal patterns. Regardless of the specific system, be it fluid dynamics, electronic circuits, or population growth, the same mathematical constants emerged. Feigenbaum's constants revealed that chaos had an underlying structure, a universality that transcended particular applications. The most fascinating aspect, Feigenbaum noted in his journal, is that these patterns appear everywhere. Nature seems to follow the same mathematical script regardless of the specific players. While these theoretical advances were unfolding, Benoit Mandelbrot was creating a visual revolution. His work on fractal geometry provided the language to describe the intricate structures that emerge in chaotic systems. The infinitely complex Mandelbrot set, with its hypnotic boundary of swirling patterns that repeated at every scale, became an icon of chaos theory. For the first time, the mathematics of chaos had a face, and it was mesmerizing. By the late 1970s, laboratory scientists began finding chaos in physical systems. Electrical circuits, chemical reactions, lasers, fluid dynamics, all exhibited the fingerprints of chaos under certain conditions. The theory wasn't just abstract mathematics. It described real physical phenomena that could be observed and measured. As the 1980s dawned, chaos theory began spreading beyond physics and mathematics. Robert May, an Australian ecologist, demonstrated that even the simplest population models could produce chaotic dynamics. His difference equation xt plus 1 equals r, x, open parenthesis, 1 minus x, close parenthesis, showed that a straightforward model of animal population growth could yield stable populations, regular oscillations, or complete chaos, depending solely on the value of a single parameter r. Even the simplest nonlinear systems, May wrote, can produce behaviors so complex as to appear random. The implications were profound. If such simple ecological models could produce chaos, Then perhaps unpredictability was woven into the fabric of nature itself. Biologists began finding chaotic patterns in real ecosystems. From fish populations to insect outbreaks, medicine followed. Researchers discovered that healthy heartbeats aren't perfectly regular, but exhibit chaotic variations. Too much regularity in a heartbeat was actually a warning sign of cardiac disease. In neuroscience, the complex firing patterns of neurons revealed chaotic dynamics. The human body, it seemed, wasn't a perfect machine but a chaotic system expertly balanced on the edge between order and disorder. In 1984, the Santa Fe Institute was founded, bringing together scientists from diverse fields to study complex systems. Chaos theory began evolving into the broader framework of complexity science, examining how order emerges from chaos, how simple rules generate complex behaviors, and how systems adapt and evolve. By 1987, chaos theory had captured enough scientific imagination to warrant broader attention. James Gleick, a science writer for the New York Times, published Chaos: Making a New Science, a book that catapulted chaos theory into public consciousness. Suddenly, the butterfly effect and fractals entered popular discourse. Chaos wasn't just for specialists anymore. It had become part of how we understand the world. Through the 1990s and beyond, chaos theory matured from revolutionary insight to standard curriculum. University textbooks incorporated nonlinear dynamics and chaos. Engineering schools taught students how to recognize and sometimes harness chaotic behavior. The once radical notion that deterministic systems could behave unpredictably had become scientific orthodoxy. The evolution continued as researchers explored quantum chaos, the peculiar intersection of quantum mechanics and classical chaos theory. Others developed sophisticated techniques for analyzing nonlinear time series data, detecting chaos in everything from stock markets to climate records. Looking back from her penthouse office, Dr. Eleanor Harding, mathematician and chaos theorist, reflected on this remarkable journey as she prepared her lecture for the International Congress of Mathematicians. "What fascinates me most," she said to her assistant, "is not just the science, but the human story. How could Poincaré see so clearly in 1890, yet the world needed 70 years to catch up? It wasn't just about mathematical insight. We needed computers to visualize what he could only imagine. We needed a scientific culture ready to embrace unpredictability as a fundamental feature of deterministic systems." She walked to the window, gazing at the city lights below, each one representing a life following its own trajectory, unpredictable, yet bounded by invisible attractors. "Chaos theory didn't emerge in a vacuum," she continued. "It had champions and skeptics, believers and critics. It formed communities that crossed traditional boundaries. Mathematicians talking to meteorologists, physicists collaborating with biologists. Perhaps that's its greatest legacy, reminding us that nature doesn't respect our artificial divisions of knowledge." Outside, lightning flashed across the sky, illuminating storm clouds, whose shapes and movements followed the very equations Lorentz had discovered. In that brief illumination, one could almost glimpse the strange attractor that governed the weather, invisible but omnipresent, shaping patterns we can describe but never fully predict. The story of chaos was still unfolding, even as its pioneers passed into history. New questions emerged at the frontiers. How do chaotic systems evolve and adapt? What happens when chaos meets quantum uncertainty? Can we harness chaos for computation or control? As rain began to fall, each droplet following its chaotic trajectory from cloud to ground, Dr. Harding turned back to her notes. The past had yielded its insights through accident, intuition, and perseverance. The future would require the same human qualities, even as the mathematics grew more sophisticated and the applications more diverse. The chaos revolution had come full circle, from Poincaré's solitary insight to a global scientific enterprise, from mathematical curiosity to fundamental principle. And like the systems it described, its trajectory had been unpredictable, yet, in retrospect, somehow inevitable. The quiet hum of fluorescent lights formed the white noise backdrop to Edward Lorenz's laboratory at MIT. Outside, the Boston wind howled against the windows, but inside, the meteorologist hunched over printouts, his face illuminated by the glow of his Royal McBee computer, a machine the size of a refrigerator that consumed more electricity than most household appliances. It was 1961, and Lorenz had just stumbled upon something that should forever change our understanding of the natural world. "I just wanted to take a shortcut," he later confessed, voice tinged with the mixture of wonder and bewilderment that would become the hallmark of chaos theorists. "I rounded the numbers in my weather simulation from 6 decimal places to 3. The results should have been nearly identical. But they weren't. Not even close. The patterns diverged wildly, exponentially. A weather system that should have remained stable in the simulation instead spiraled into unrecognizable territories. What began as a rounding error, no larger than a puff of air, had transformed into a simulated hurricane. Lorenz wasn't alone in his discovery, though for years he might have felt that way. The interconnected web of mathematicians, physicists, and thinkers who would eventually coalesce into the chaos theory community was already forming, though scattered across continents, disciplines, and decades. Henri Poincaré had glimpsed it first, back in the 1890s, when the celebrated French mathematician attempted to solve the three-body problem in celestial mechanics. His elegant mind, which had conquered so many mathematical territories, found itself confronted with an unsettling truth. Some deterministic systems could behave in fundamentally unpredictable ways. The trajectories of 3 celestial bodies influencing each other through gravity could be incalculably complex. Poincaré's insights were profound but premature, a mathematical vision without the computational tools to fully explore it. His ideas slumbered in academic journals, waiting for technology to catch up. When George David Birkhoff extended Poincaré's work in the early 20th century, developing what would later be recognized as the foundations of ergodic theory, few could have predicted how these abstract mathematical concepts would eventually illuminate everything from heart rhythms to stock markets. Meanwhile, across the political divide of the Cold War, Soviet mathematicians like Andrei Kolmogorov, Dmitry Inosov, and Yakov Sinai were independently developing parallel theories, their papers circulating within the isolated intellectual ecosystem behind the Iron Curtain. We were all speaking different languages, not just Russian and English, but the languages of our respective disciplines, recalled David Ruel, the Belgian mathematical physicist, who, along with Dutch mathematician Floris Takens, would later introduce the concept of strange attractors. But we were all describing the same underlying reality. The mathematicians and physicists of chaos theory didn't work in romanticized isolation. They formed a complex network themselves, collaborating, competing, sometimes contradicting one another. Stephen Smale, with his disheveled hair and penetrating gaze, revolutionized dynamical systems theory in the 1960s, creating mathematical frameworks that would later help explain everything from turbulent fluid flow to the electrical patterns of cardiac arrhythmia. When Smale received the Fields Medal, mathematics' highest honor, in 1966, few outside his field understood the significance of his topological approaches to dynamics. Within 2 decades, his work would help explain phenomena as diverse as dripping faucets and population crashes. Mitchell Feigenbaum, chain-smoking his way through long nights at Los Alamos National Laboratory in the mid-1970s, discovered something even more astonishing: universality. Using nothing more sophisticated than a pocket calculator, Feigenbaum found that completely different chaotic systems, from electronic circuits to chemical reactions, followed identical mathematical patterns as they transitioned from order to chaos. The Feigenbaum constants, as they came to be known, suggested something profound. Chaos had its own internal order, its own laws. The same mathematical skeleton structured apparently unrelated systems across the natural world. I remember Mitch coming into my office, sleep-deprived but electrified, a colleague later recalled. He kept saying, "It's the same number. It's always the same number." We thought he might have lost his mind until we saw the evidence. While the pure mathematicians built the theoretical foundations, applied scientists began discovering chaos in the world around them. Robert May, an Australian theoretical physicist turned ecologist, demonstrated in the 1970s that even the simplest population models could produce chaos. His logistic map, originally used to model fish populations, revealed that the boundary between order and chaos was far thinner than anyone had realized. Even rabbits can behave chaotically, May would quip during lectures, referring to how simple predator-prey relationships could generate patterns of bewildering complexity. Benoit Mandelbrot, with his French-accented English and penetrating insights, gave chaos its visual language through fractals. His famous question, "How long is the coast of Britain?" illuminated the revolutionary concept of fractal geometry. The answer, paradoxically, depended on how closely you looked. Zoom in on any coastline, and more detail emerges, more inlets and outcroppings appear. The measured length increases. This self-similarity across scales became the hallmark of fractal structures, from fern fronds to stock market fluctuations. The bearded, imposing figure of James York, the mathematician who actually coined the term chaos theory in a 1975 paper, bridged pure and applied mathematics. Alongside Edward Ott and Celso Graboghi, York later pioneered methods for controlling chaos, demonstrating that chaotic systems, while unpredictable in detail, could sometimes be nudged toward desired behaviors with tiny, precisely timed interventions. "The public thinks chaos means total disorder," York once said, his voice carrying the slight Maryland accent that decades of academic life hadn't erased. But we use the word very differently. For us, chaos is a kind of order without periodicity. Not everyone embraced the chaos revolution. Across university departments and research institutions, skeptics raised legitimate concerns. In economics, Established econometricians argued that financial markets were stochastic, not chaotic, genuinely random rather than deterministically unpredictable. The distinction was subtle, but crucial. If markets were chaotic, their future states were theoretically determined by present conditions, just practically unpredictable. If truly stochastic, no amount of information about the present could precisely determine the future. "Show me the evidence," demanded one prominent Wall Street quantitative analyst. "I see lots of beautiful mathematics, but where's the proof that this applies to real markets?" Engineers, particularly those working in noisy real-world environments, often emphasized robustness over chaos. These elegant models fall apart when you add even small amounts of noise, argued one aerospace engineer. And the real world is nothing but noise. Philosophers and methodologists cautioned against overgeneralization, warning that chaos had become an intellectual fashion that risked being applied too broadly, too carelessly. "Not everything that appears complex is chaotic in the technical sense," wrote one philosopher of science. "And not everything that's chaotic is meaningful for human affairs." These weren't deniers of chaos theory's mathematical validity. They were minimalists, people who accepted the equations but questioned the expansive interpretations and applications that followed. As chaos theory developed from mathematical curiosity to scientific paradigm, institutions emerged to support its growth. The Santa Fe Institute, founded in 1984, became the intellectual home for complexity science, gathering physicists, biologists, economists, and computer scientists under one roof in the high desert of New Mexico. There, amid adobe buildings and desert landscapes, researchers developed agent-based models, genetic algorithms, and network theories that extended chaos into new territories. "We were creating a new kind of science," recalled one early Santa Fe Institute fellow. "Not physics, not biology, not economics, but something that transcended traditional boundaries. A science of complex systems." Academic journals like Chaos and Physica D became the formal channels of communication for the growing field. Professional societies organized interdisciplinary workshops where mathematicians could talk to cardiologists, meteorologists could engage with economists. The language of chaos, phase space, bifurcations, Lyapunov exponents, gradually seeped into scientific discourse across disciplines. In the public sphere, science writers translated these complex ideas for broader audiences. James Gleick's 1987 book, simply titled Chaos, became an unexpected bestseller. Its black cover with a Mandelbrot set fragment instantly recognizable on bookshelves. Television documentaries featured swirling computer visualizations set to dramatic music. Later, YouTube channels and online educators would create mesmerizing visualizations of double pendulums and fractal zooms that accumulated millions of views. Fiction writers and filmmakers found inspiration in chaos concepts. Michael Crichton's Jurassic Park used chaos theory as a central theme, with the character Ian Malcolm serving as chaos theory's fictional prophet, warning about the unpredictability of reintroducing dinosaurs to the modern world. "Life finds a way," he intoned in the film adaptation, encapsulating the unpredictable emergence that chaos theorists observed in complex systems. The essence of chaos theory's development wasn't lone genius, but convergent discovery, multiple minds arriving at similar insights through different paths. The meteorologist Lorentz, the mathematician Smale, the physicist Feigenbaum, the geometer Mandelbrot. the ecologist May. Each contributed crucial pieces to a puzzle that no single discipline could solve alone. We were all coming from different fields, reflected one veteran of the chaos revolution, yet finding the same patterns. It felt like discovering a hidden language that nature had been speaking all along, one that crossed the artificial boundaries we'd created between physics and biology, mathematics and meteorology. This interdisciplinary character gave chaos theory its strength, but also created tensions. Different fields had different standards of evidence, different methodologies, different languages. What constituted proof for a mathematician might seem hopelessly abstract to a biologist. What an economist considered significant might seem trivial to a physicist. As night fell over university campuses and research institutions around the world, lights remained on in scattered windows where these diverse scholars worked, separated by geography and discipline, but united by a common fascination with the border territory between order and unpredictability. Their collective efforts revealed a profound truth. Deterministic systems could generate behaviors so complex that prediction became practically impossible. Yet patterns still emerged within the apparent randomness. The conversation continues today, in online forums and academic conferences, in research labs and classroom demonstrations. The core insights of chaos theory, sensitivity to initial conditions, the emergence of complex behavior from simple rules, the fractal geometry of nature, have become part of our intellectual heritage, changing how we understand everything from weather forecasting to cardiac arrhythmias, from traffic patterns to ecological networks. The actors in this scientific drama, with their different perspectives and contributions, collectively transformed our understanding of complexity. They showed us that unpredictability doesn't necessarily mean randomness, that determinism doesn't guarantee predictability, and that the boundary between order and chaos is not a wall, but a fascinating frontier, one that continues to yield new insights as we explore its contours. The sleek ebony desk caught a sliver of moonlight as Gabriel Rothwell leaned back in his Herman Miller chair, allowing his gaze to drift across the panorama of Manhattan from his 57th floor office. The ambient lighting of his private library cast long shadows across leather-bound volumes of philosophy and scientific journals. He traced a finger absently along the spine of Laplace's A Philosophical Essay on Probabilities, remembering his grandfather's words about knowledge and power. "Everything that exists," Gabriel murmured to himself, "follows from what came before." That was Laplace's vision, his demon. He retrieved the book, turning carefully to a dog-eared page. Pierre-Simon Laplace had proposed a thought experiment in 1814 that had haunted scientific discourse ever since. Gabriel recited the passage as if it were poetry. An intellect which at a certain moment would know all forces that set nature in motion, and all positions of all items of which nature is composed, would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. The antique grandfather clock in the corner of his study chimed midnight. Gabriel poured himself 2 fingers of Macallan 25, savoring its amber glow in the crystal tumbler. Such certainty that Laplace had offered, a universe of perfect clockwork. If one knew every position, every momentum of every particle, one could predict the entire future and reconstruct the entire past. Yet Gabriel knew the flaw that Laplace couldn't have foreseen. Even his demon would fail, not because determinism was wrong, but because the demon would need infinite precision. The tiniest error in measurement, off by a billionth of a billionth, would explode exponentially. Errors cascade. Small differences amplify. "The butterfly effect," Gabriel whispered, watching ice melt in his glass, creating intricate swirling patterns as it dissolved. His trading empire had been built on this understanding. While others saw markets as either rational or random, Gabriel recognized them as chaotic systems, deterministic, yet fundamentally unpredictable beyond short timescales. The intercom buzzed, and his assistant's voice filtered through. "Dr. Winters has arrived, Mr. Rothwell." "Send her in, Elise." Alexandra Winters entered with the confident stride of someone comfortable in rarefied spaces. Her doctoral work at Princeton on quantum field theory had caught Gabriel's attention 3 years ago. Now she headed his Foundation's Theoretical Physics Division. "You wanted to discuss the Copenhagen interpretation?" She settled into the leather armchair opposite his desk, declining his offer of scotch with a small shake of her head. "I've been thinking about the conceptual differences between chaos and quantum indeterminacy," Gabriel said, gesturing toward the Manhattan skyline. "Out there, billions of interactions occurring simultaneously, some fundamentally random, others merely unpredictable." Alexandra nodded. "A crucial distinction. In quantum mechanics, the electron's position is fundamentally uncertain until measured. Intrinsic randomness built into the universe's foundation. Chaos, by contrast, is deterministic but unpredictable. In one, God plays dice," Gabriel mused. "In the other, God plays with loaded dice. But they're so sensitive to the slightest touch that no one can track them." "Precisely." Alexandra's eyes lit with intellectual passion. "Quantum systems possess genuine randomness. Chaotic systems are deterministic, but exquisitely sensitive to initial conditions. The implications for information theory alone are staggering." Gabriel rose and approached a glass cabinet in the corner. He unlocked it with a small key from his pocket and retrieved an ancient text bound in faded silk, a rare 14th century Taoist manuscript he'd acquired from a private collector in Shanghai. "My grandfather was fascinated by Eastern philosophical traditions," Gabriel said, carefully opening the fragile volume, "particularly those emphasizing balance, flow, and the inherent unpredictability of natural processes." Alexandra studied the delicate calligraphy. "I've read that some writers claim chaos theory validates ancient Taoist concepts." "Many have drawn that parallel," Gabriel agreed, "particularly after Capra's Tao of Physics in the 1970s. The way Taoist philosophy emphasizes dynamic balance and the complementary nature of opposites does resonate with certain aspects of complexity science." He turned to another shelf, extracting a modern academic text. "Buddhist teachings on interdependence, the idea that everything affects everything, have similarly been linked to chaos theory." A cynical smile touched his lips. The Romantic poets, too, Wordsworth, Coleridge, Blake, they rejected mechanistic reduction in favor of organic unity and the sublime unpredictability of nature. All these traditions have been retroactively claimed as chaos theory precursors. Alexandra raised a skeptical eyebrow. "But such comparisons are often superficial, aren't they? Poetic metaphor rather than mathematical equivalence." "Exactly." Gabriel returned to his desk. Chaos theory is mathematics, not mysticism. It provides equations and precise quantitative measures like Lyapunov exponents. The resemblance to ancient wisdom traditions is intriguing but ultimately metaphorical. Taoist sages didn't calculate phase space volumes or basin boundaries. The room fell silent, save for the subtle ticking of the grandfather clock. Outside, clouds drifted across the waxing moon, casting the city into momentary shadow. "What about cybernetics?" Alexandra asked, breaking the contemplative silence. "Norbert Wiener's work seems directly ancestral to complexity science." Gabriel nodded appreciatively. "Absolutely. Cybernetics introduced crucial concepts, feedback loops, homeostasis, self-regulation, that became foundational for chaos theory. Wiener understood that systems with feedback behave in ways that simple linear analysis can't capture. He moved to a wall-mounted touchscreen and pulled up a series of images. Complex circuit diagrams, early computer simulations, mathematical equations. "But we can trace even earlier roots," he continued. "Celestial mechanics and perturbation theory in the 19th century grappled with the three-body problem, the impossibility of solving exactly for the motion of three gravitationally interacting bodies." Poincaré's work here was revolutionary, though largely ignored for decades. Alexandra rose to examine a framed equation on Gabriel's wall, a famous formula from nonlinear oscillation theory developed in the early 20th century. "And here we have van der Pol and his relaxation oscillators," Gabriel explained. "Early examples of nonlinear systems exhibiting complex behavior. Then statistical mechanics introduced concepts of criticality, universality, and scaling. The recognition that systems near critical points display similar behaviors, regardless of their microscopic details." Outside, a distant thunderstorm was approaching, lightning occasionally illuminating the Manhattan skyline in brief electric flashes. "What fascinates me," Alexandra said, watching the storm's progress, "is how these intellectual traditions converged from such different starting points. Meteorologists like Lorenz, mathematicians like Smale, physicists like Feigenbaum, all discovering pieces of the same puzzle independently." Gabriel nodded, refilling his glass. "That convergence suggests something fundamental about nature itself. The universe seems to operate in ways that generate complexity from simple rules. Whether we're looking at weather patterns, fluid turbulence, or heart rhythms," a sharp crack of thunder punctuated his words, followed by the sudden drumming of rain against the floor-to-ceiling windows. "I've commissioned a series of essays," Gabriel said, handing Alexandra a leather portfolio, "exploring the transition from classical determinism through chaos to quantum uncertainty. I'd like your input, particularly on the problems of classical quantum correspondence in chaotic systems." Alexandra accepted the portfolio with evident interest. The semi-classical limit in chaotic systems remains one of physics' most tantalizing frontiers. When quantum effects meet chaotic dynamics, our conventional mathematical tools begin to fail us. Gabriel walked to the window, watching raindrops create intricate, unpredictable patterns as they streamed down the glass. "That's where we find the most profound questions. How does quantum uncertainty interfere with chaotic unpredictability? Is the universe fundamentally random, merely unpredictable, or something else entirely?" The storm intensified, lightning now flashing in rapid succession across the city skyline. In that stroboscopic illumination, The patterns of raindrops seem to freeze momentarily before resuming their chaotic descent. There's a quote from Henri Poincaré I've always found compelling, Gabriel said softly. It may happen that small differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible. Alexandra joined him at the window. Yet despite that impossibility, patterns emerge. Strange attractors, islands of stability in seas of chaos. That's the paradox, Gabriel agreed. Deterministic unpredictability coexisting with emergent order. The universe writes in a language we're still learning to read. They stood in comfortable silence, watching the storm gradually move eastward over the Atlantic, leaving behind a glistening city and clearing skies. The first stars became visible, their ancient light reaching Earth after journeys of incomprehensible duration. The intellectual roots of chaos theory reveal something profound about human knowledge itself, Gabriel said finally. We've moved from Laplace's perfect determinism through chaos's bounded unpredictability to quantum uncertainty, each paradigm encompassing and transcending the last, not replacing, but complexifying. Alexandra smiled, suggesting perhaps that our next scientific revolution won't invalidate chaos theory, but situate it within something even more comprehensive. Precisely. Gabriel raised his glass in a small toast. To intellectual traditions, and to the questions that remain. As they continued their discussion deep into the night, the patterns of stars wheeled slowly overhead, following trajectories both perfectly determined and practically unpredictable. Celestial scribes writing equations of cosmic complexity across the vault of heaven. The chandelier scattered diamonds of light across the mahogany table as Alexander Whitfield's elegant fingers traced the edge of his leather-bound notebook. The room smelled of sandalwood and aged paper. His private library at Whitfield Manor, where fortunes were contemplated and decisions that moved markets were made. The question that haunts me, he said, his voice carrying the weight of a man who had built empires on prediction, is where certainty ends and chaos begins. His guest, Professor Eleanor Chen, adjusted her wire-rimmed glasses, the golden light catching the silver in her otherwise jet-black hair. Her reputation as a mathematician preceded her, having spent decades studying the mathematics of unpredictability. That's precisely why I've asked you here, Alexander continued. My analytics team claims they can predict everything from consumer behavior to currency fluctuations. But recently, their models have failed spectacularly. He slid a graph across the polished surface. I need to understand where the line is. Where can we trust our predictions, and where do we enter the domain of chaos? Eleanor nodded, taking the graph with slender fingers adorned with a single jade ring, her only concession to ornamentation. Let me show you where we stand on solid ground, she said, opening her laptop. The blue light illuminated her face as she brought up a series of mesmerizing patterns. In mathematics, chaos isn't theoretical, it's proven. The logistic map, the Lorentz system. These aren't hypotheses or conjectures. They're theorems with rigorous proofs behind them. Alexander leaned forward, captivated by the swirling patterns on the screen. What appeared random revealed itself as structured, a strange attractor forming a butterfly pattern that never repeated, yet never escaped its invisible boundaries. These patterns, Eleanor continued, her voice taking on a professor's cadence, aren't just mathematical curiosities. They've been reproduced in laboratory settings across disciplines. She switched to a video of a peculiar chemical experiment, the Belousov-Zhabotinsky reaction. Colors pulsed through the liquid in spiraling patterns, oscillating in ways that seemed both random and ordered simultaneously. In lasers, in electronic circuits, in chemical reactions like this one, researchers have measured the telltale signatures of chaos: Lyapunov exponents, fractal dimensions, strange attractors. The evidence is reproducible and overwhelming. The room grew quieter as she continued, the only sound the occasional crackle from the fireplace and the soft patter of rain against the windows. And in weather, she said, bringing up a new visualization, Edward Lorenz's fundamental insight holds true 50 years later. Forecasts degrade exponentially. Beyond 2 weeks, precision collapses entirely. This is chaos in action, the butterfly effect, made manifest in our daily weather reports. Alexander's eyes narrowed. So the meteorologists, who can't tell me if it will rain on my vineyard next month, that's not incompetence? Not at all. It's a fundamental limit of predictability. Weather is a chaotic system, and the most sophisticated models in the world hit the same wall. They've adapted by using ensemble forecasting, running dozens of slightly different initial conditions to see the range of possibilities. But precise prediction beyond the horizon, impossible. Alexander poured them both a glass of amber scotch, the bottle worth more than most people's monthly salary. Yet this is where my confusion begins, Eleanor. If chaos is so well established, why do I hear such conflicting things about its application to markets? The professor took a small sip, appreciating the smoky complexity before answering. Now we enter more ambiguous territory. In finance and economics, researchers have conducted extensive tests, calculating correlation dimensions using surrogate data methods, applying nonlinear prediction techniques. She pulled up a series of financial time series, stock markets, currency exchanges, commodity prices. Some researchers find hints of chaotic dynamics, but the mainstream consensus? Markets are better modeled as stochastic processes with complex structure, not as low-dimensional deterministic chaos. Why the difference? Alexander asked, his fortune built on understanding such distinctions. The data are too short, too noisy, too contaminated by human intervention. Markets change their fundamental character over time. They're non-stationary. And critically, there's genuine randomness in market systems. News events, natural disasters, technological breakthroughs that isn't present in purely deterministic chaos. Alexander's face fell slightly. So my analysts claiming they can detect market chaos and predict turning points are likely overselling, Eleanor finished gently, though nonlinear approaches still have value. The grandfather clock in the corner chimed 11 as they moved to leather armchairs near the fireplace. Outside, the coastal storm intensified, waves crashing against the cliffs below the estate. What about biological systems? Alexander asked, his interest now purely intellectual rather than financial. My physician mentioned chaos theory in relation to heart rhythms during my last physical. Eleanor nodded, warming to the topic. Another fascinating but complicated area. Healthy heart rhythms show complex variability, possibly chaotic. Disease often reduces this complexity. Researchers can measure what's called loss of complexity in aging and illness. She pulled up a comparison of heartbeat intervals, one showing rich variability, another more regular, but somehow less healthy looking. But is it literally low-dimensional chaos in the mathematical sense? Or just high-dimensional complexity, with both deterministic and random components? The evidence is mixed. Similar questions arise with brain activity, especially around epileptic seizures. Some evidence suggests seizures represent a transition from chaotic to more ordered dynamics. Alexander watched the dancing flames, contemplating. And ecosystems? Population crashes? Laboratory insect populations show clear chaotic dynamics under certain conditions. The evidence there is strong. But wild ecosystems? Eleanor shrugged slightly. Plausible, but not proven. We lack the long, clean time series needed, and can't rule out environmental noise and multi-species interactions. The patterns look chaotic, but definitively proving it is another matter entirely. The wind howled outside as Alexander rose, walking to his wall of windows overlooking the turbulent ocean below. I've heard chaos theory invoked to explain everything from the fall of civilizations to individual destiny, that every small action changes history, that the flutter of a butterfly's wings in Brazil causes a tornado in Texas. Eleanor joined him at the window, her reflection ghost-like against the darkness beyond. Now you've touched on what troubles me most as a mathematician. The metaphorical overreach. Claims that chaos theory proves free will, that it explains the entire human condition, that it governs markets, societies, and minds in the technical sense. Not valid, Alexander asked. Most are poetic, not scientific. They borrow the language of chaos without the rigor. The butterfly effect is real in weather systems. Yes, but that doesn't mean every small action literally changes world history. That's taking a mathematical concept and stretching it beyond recognition. Lightning illuminated the coastline momentarily, the jagged electricity mirroring the chaotic patterns they had been discussing. So where does that leave us? Alexander asked, his voice quieter now. What can I trust? Eleanor considered carefully. Trust the mathematics. Trust the laboratory results. Trust the application to weather forecasting, with its known limits. Be cautious about claims in finance, biology, and ecology. There's something there, but often not what's claimed. And be highly skeptical of applications to history, society, and individual lives. She turned to face him directly. The most honest position? In controlled systems, chaos is proven. The math is airtight. But as you move to real-world complex systems, the evidence becomes progressively weaker, and distinguishing chaos from randomness becomes nearly impossible. Alexander nodded slowly, his wealth built on knowing when certainty ended and probability began. That's clarifying, if somewhat disappointing. There's another challenge, Eleanor added, returning to her seat. Methodological limitations. Even with perfect data, our techniques for detecting chaos have biases. Short datasets overestimate dimensions. Noise contaminates Lyapunov exponents. And non-stationarity. Systems that change their fundamental character over time wreaks havoc with all detection methods. The fire crackled in counterpoint to their conversation, sending shadows dancing across the book-lined walls. A researcher named James Thieler demonstrated this brilliantly, she continued. He took purely random noise, embedded it in a certain way, and showed that naive methods would incorrectly detect chaos. It was a wake-up call to the field. Alexander smiled ruefully. I suspect some of my analysts need that wake-up call. The irony is that chaos theory teaches us about the limits of prediction, Eleanor said, finishing her scotch. Yet it's often invoked to claim special predictive power. That's the fundamental contradiction. They sat in comfortable silence for a moment, two minds appreciating the complexity of knowledge itself, where certainty faded into probability and probability into possibility. What interests me most, Alexander said finally, is how different fields view chaos. A mathematician sees elegant proofs, a physicist sees universal patterns, an engineer sees systems to stabilize. I imagine economists, biologists, and philosophers all see something entirely different in these same equations. Eleanor's eyes lit up. That's precisely what makes chaos theory so fascinating across disciplines. The mathematician, the physicist, the biologist, they're looking at the same phenomenon through different lenses, and sometimes they're barely speaking the same language. Outside, the storm began to subside, the chaos of the weather system dissipating into the ordered calm that would follow by morning. Alexander Whitfield made a note in his journal, a reminder that in both wealth and knowledge, knowing the boundaries of certainty was perhaps the greatest wisdom of all. The Harrington estate perched on a limestone cliff overlooking the Atlantic, its walls of glass reflecting the moonlight, like a crystalline structure born from the coast itself. Within its mathematical precision of right angles and perfect symmetries, Theodore Harrington III stood before his wall of monitors, each displaying a different manifestation of the same phenomenon. Chaos, he whispered, his breath fogging the glass of cognac held loosely in his right hand. The screens before him pulsed with life, fractals spiraling into infinite complexity, weather patterns evolving across continents, stock market fluctuations rendered as undulating landscapes of potential. A fortune built on understanding what others saw as random. His assistant, Dr. Maya Chen, entered silently, her footsteps absorbed by the plush carpeting. The conference call is ready, Mr. Harrington. All 6 specialists are waiting. Theodore nodded, setting down his glass on a marble coaster etched with the Lorenz attractor, his personal emblem. The screens before him shifted to reveal 6 faces, each illuminated by the cold light of academic offices scattered across the globe. Let us continue our exploration, Theodore said, his voice carrying the quiet authority of extreme wealth. I've assembled you all, the finest minds across disciplines, because I believe chaos theory represents not just a scientific paradigm, but perhaps the most profound lens through which we might understand existence itself. Professor Eleanor Whitman, a mathematician whose chalk-dusted fingers betrayed her preference for traditional proofs over computational models, spoke first. Mr. Harrington, while your enthusiasm is commendable, we must be precise. In mathematics, chaos isn't some mystical force. It's a rigorous framework built on dynamical systems, topology, and measure theory. Her screen filled momentarily with equations, elegant in their abstraction. We care about invariance, she continued, quantities that remain constant despite a system's evolution. Lyapunov exponents that measure sensitivity to initial conditions, entropy values that quantify information generation, fractal dimensions that characterize strange attractors. And renormalization, added Professor Katsaros, a Greek mathematician with silver temples and intense eyes. The discovery of universality, that entirely different systems exhibit identical scaling behaviors when approaching chaos. That was revolutionary. Theodore nodded appreciatively. Yet physicists seem to approach chaos differently. Indeed, Dr. James Takahashi responded, adjusting his wire-rimmed glasses. His laboratory at MIT specialized in quantum chaos. Mathematicians seek proofs. We seek physical manifestations. Classical chaos appears everywhere. Celestial mechanics, fluid dynamics, plasma physics. But the quantum realm presents fascinating paradoxes. Quantum chaos, Theodore murmured. The contradiction at the boundary of theories. Not quite a contradiction, Takahashi corrected gently, but certainly a fascinating frontier. We examine spectral statistics, quantum scars, patterns of probability that echo classical chaotic trajectories, and semi-classical limits where quantum and classical behaviors meet. And turbulence? Theodore inquired. The ultimate high-dimensional chaotic system, Takahashi confirmed. The greatest unsolved problem in classical physics, as some call it. A cascade of instabilities across scales. The conversation shifted as Theodore gestured toward another screen, where a woman with practical, short-cropped hair waited patiently. Dr. Harrison, how do engineers view chaos? Not as a problem to understand, but to utilize, I presume. Dr. Harrison smiled. Precisely. We're pragmatists. We've developed methods to control chaos in circuits and lasers, small perturbations that can stabilize unstable orbits. We exploit chaotic advection for efficient mixing technologies, from industrial processes to microfluidics devices that revolutionized medical diagnostics. And encryption? Theodore asked. His interest piqued. He hadn't amassed his fortune without understanding security. An interesting case, Dr. Harrison replied. There were many proposals for chaos-based encryption in the 1990s and early 2000s. The sensitivity to initial conditions seemed perfect for cryptography. However, most systems proved vulnerable to attacks, and the field has seen limited adoption compared to conventional cryptographic standards. Theodore nodded thoughtfully. Moving to natural systems, Dr. Okafor, your perspective as an earth scientist? Dr. Nkichi Okafor adjusted her position, Lagos visible through her office window. Meteorology embraced chaos theory perhaps more thoroughly than any other field. Edward Lorenz's discovery fundamentally changed weather prediction. We now use ensemble forecasting, running multiple simulations with slightly different initial conditions to generate probability distributions rather than single predictions. And climate science? Theodore asked. A different challenge entirely, Dr. Okafor continued. Climate involves longer timescales and additional complexities, but chaos remains central to understanding predictability limits and identifying potential tipping points. And in living systems? Theodore asked, turning to Professor Gabriela Santos, whose background in theoretical ecology had earned her both a Fields Medal and unexpected celebrity. Ecological and epidemiological systems show fascinating chaotic dynamics, Professor Santos explained. Population cycles that appear random but follow deterministic rules. Disease outbreaks whose timing becomes unpredictable beyond short horizons. Even within our bodies, cardiac rhythms, neural activity, endocrine systems, chaos appears to be not a malfunction, but an essential feature enabling adaptability. Theodore sipped his cognac, savoring its complexity. Yet economics seems resistant to chaos theory's advances. Dr. Lawrence Chen, chief economist at a prestigious investment bank, cleared his throat. There were many attempts to detect chaos in market data and macroeconomic variables in the 1990s. The results remain controversial. Most mainstream economics favors stochastic models, incorporating explicit randomness over deterministic chaos. Why? Theodore challenged, his eyes narrowing slightly. Several reasons, Dr. Chen replied. Stochastic models often fit empirical data better. They're more mathematically tractable, and frankly, they're more compatible with existing theoretical frameworks. Agent-based modeling and complex adaptive systems approaches incorporate some chaos-inspired ideas, but they remain somewhat peripheral to mainstream economics. Theodore nodded, unsurprised. His own fortune had been built partly on recognizing patterns others dismissed as random, exploiting the narrow gap between determinism and unpredictability. "And what of philosophy?" Theodore asked, turning to Professor Eliza Montague, whose book on causality in complex systems had sparked considerable controversy. Does chaos theory change how we understand reality itself? Professor Montague's austere office, lined with leather-bound volumes, seemed to belong to another century. Chaos theory revitalizes ancient philosophical questions. It forces us to distinguish between determinism and predictability. Laplace's demon, that hypothetical intelligence capable of calculating the entire future from complete knowledge of the present, fails not because determinism is false, but because perfect measurement is impossible. The room fell silent as she continued. Chaos theory enters the free will debate by creating space for agency within deterministic systems. It transforms our understanding of causation, explanation, and counterfactuals. What does it mean to explain a phenomenon we cannot predict? How do we assign responsibility in systems where microscopic differences produce macroscopic divergences? And what of emergence? Theodore asked. The whole greater than its parts. Exactly, Professor Montague nodded appreciatively. Chaos theory challenges both strict reductionism and holism. Complex systems exhibit emergent properties not obvious from their components. Yet these emerge through deterministic interactions, not mystical wholeness. Theodore turned finally to the last participant, Father Dr. Michael Ignatius, a Jesuit physicist whose work on reconciling science and faith had earned both acclaim and criticism. And spirituality, Father Ignatius? How does religion respond to a universe where God's creation seems simultaneously determined and unpredictable? The priest smiled gently. Various traditions have different responses. Some theologians see chaos as evidence of divine inscrutability. God's creation is too complex for human minds to fully comprehend. Providence operates through what appears to us as chance or chaos. Fascinating, Theodore murmured. Eastern traditions, particularly Taoism, and certain Buddhist philosophies, find resonance with chaos theory's emphasis on impermanence, interconnectedness, and the balance between order and disorder. Father Ignatius continued. The New Age movement enthusiastically embraced chaos theory, often speaking of cosmic chaos and universal interconnectedness, though not always with scientific rigor, Professor Whitman interjected dryly. Indeed, Father Ignatius acknowledged. There are scholarly critiques of physics-spirituality syntheses that appropriate scientific terminology without honoring its precise meaning. Chaos theory is mathematics, not metaphysics. These appropriations are often more poetic than precise. Theodore gazed at the assembled experts, their faces illuminated by the cold light of screens. Mathematicians, physicists, engineers, earth scientists, biologists, economists, philosophers, theologians, each framing chaos through their disciplinary lens. The concept stretched between them, elastic, transformed by perspective. "What strikes me," Theodore said finally, "is that chaos means something different to each of you. To the mathematician, it's a precise definition involving sensitive dependence. To the physicist, it's a measurable phenomenon. To the engineer, it's something to control or exploit. To the earth scientist, it's a constraint on prediction. To the biologist, it's a feature of living systems. To the economist, it's mostly a footnote. To the philosopher, it reopens ancient questions. To the theologian, it's another natural phenomenon requiring interpretation." He stood, moving to the wall of windows overlooking the restless Atlantic. Moonlight scattered across the waves, each reflection a momentary cipher impossible to track, yet governed by laws as old as the universe. "Is chaos theory unified or fragmented?" he asked, not turning from the view. "Is it one concept or many?" Professor Whitman answered first. "The mathematical foundation is singular and rigorous. The applications and interpretations are diverse." "Chaos is beautiful," Dr. Takahashi added, "but it's not magic." "We tried chaos models in economics," Dr. Chen admitted. "They didn't forecast better than stochastic ones." "Chaos shows determinism doesn't guarantee predictability," Professor Montague reflected. "That's profound, but it doesn't solve the free will problem." Theodore turned back to face them, his silhouette outlined against the vast darkness of the ocean and sky. "If chaos is so contested in theory, what has it actually changed in the world? What have people done because of chaos theory? How has it shaped not just ideas, but actions?" As the experts began to answer, Theodore glanced at Maya, who stood silently by the door. She gave him an almost imperceptible nod. The true purpose of tonight's gathering remained hidden from these luminaries. The application of their collective insights to a project that would either secure the Harrington legacy for generations or destroy it entirely. The butterfly protocol, they called it internally. An algorithm that discovered order within apparent randomness, prediction within the unpredictable, deployed across markets and systems previously thought impervious to forecasting. The ultimate arbitrage of uncertainty. Outside, lightning flashed across distant clouds, illuminating countless possible paths for the storm to follow. Thunder followed seconds later, its low rumble a reminder that even chaos obeys fundamental laws, if one only knows how to listen. The snowflakes fell slowly outside the floor-to-ceiling windows of Dr. Elaine Westover's penthouse overlooking Central Park. She sat in her custom Eames chair, bathed in the soft glow of her desk lamp, reviewing data on her holographic display. The blue light illuminated her face as she studied the complex patterns of heart rate variability across multiple patients. "Fascinating," she whispered, taking a sip of her single malt scotch. At 62, Elaine had become one of the wealthiest cardiologists in Manhattan, not just through her medical practice, but through her pioneering work in nonlinear cardiac diagnostics. 20 years ago, when she'd first proposed using chaos theory to analyze heart rhythms, her colleagues had laughed. Now her company, Westover Medical Systems, supplied diagnostic algorithms to hospitals worldwide. The intercom chimed softly. "Dr. Westover, your 7 o'clock has arrived. Send him up, please." Minutes later, Professor James Chen entered, brushing snowflakes from his cashmere coat. He was younger than Elaine by almost 2 decades, but his reputation in computational biology preceded him. "Terrible weather," he remarked, accepting the glass she offered. "But I suppose that's fitting for our conversation tonight." "Weather forecasting," Elaine smiled. "The original triumph of chaos theory in the real world." "Indeed." James settled into the leather sofa. "Though sometimes I wonder if meteorology's success has been both a blessing and curse for the rest of us, trying to apply these principles elsewhere." Elaine nodded thoughtfully. The ensemble approach revolutionized forecasting, running hundreds of simulations with slightly different initial conditions, seeing where they converge or diverge. Perfect for weather, much harder to implement in medicine. Outside, the snow had intensified, transforming the Manhattan skyline into a blur of lights and shadow. The two scientists gazed at the scene momentarily, both contemplating how chaos theory had reshaped their respective worlds. "I visited the Complexity Sciences Center at Princeton last week," James said, breaking the silence. "Their new computational wing is remarkable. Interdisciplinary teams, physicists working alongside ecologists, mathematicians collaborating with neuroscientists. The field has certainly grown beyond its origins," Elaine agreed. "When I was in medical school, these disciplines barely acknowledged each other. Now we have entire institutes dedicated to complexity." She walked to her desk and pulled up another holographic display, this one showing the intricate patterns of a strange attractor. "My latest project," she explained. "We're attempting to use these patterns to predict seizures in epilepsy patients. The mathematics suggest there should be warning signals before a major event, subtle changes in brainwave complexity that conventional EEG analysis misses." James studied the rotating pattern with interest. "And has it been clinically validated?" Elaine's expression dimmed slightly. "That's the challenge, isn't it? The models are compelling, the mathematics sound, but the clinical evidence—" She sighed. "It's proving more difficult than we anticipated to translate chaos control techniques from the laboratory to actual patients." "The gap between theory and practice," James nodded. "I see it in my field as well." The conversation paused as Elaine's assistant brought in a tray of appetizers, delicate canapes from her favorite chef downtown. "Speaking of gaps between theory and practice," James continued, selecting a morsel, "have you followed what's happening in finance since the 2008 crisis?" Elaine smiled wryly. "How could I not? My portfolio certainly felt the butterfly effect." "The rhetoric changed overnight," James observed. "Suddenly everyone in finance was talking about complexity, systemic risk, cascade effects, tipping points, borrowing language from our field without necessarily adopting the mathematical rigor." "Fashion tends to follow disaster," Elaine replied. "After the crisis, it became clear that traditional risk models had failed catastrophically. Value at risk calculations, Gaussian copulas, they all assumed linear, well-behaved distributions. And reality proved stubbornly nonlinear." "Precisely." Elaine refilled their glasses. "Though I find it somewhat amusing how selectively they've embraced chaos concepts. The finance world loves talking about black swans and fat tails now. but their day-to-day models are still largely stochastic, not truly chaotic. Through the windows, they could see the lights of the financial district glimmering in the distance, partially obscured by the snowfall. My son works at Goldman, Elaine continued. He tells me there's a fundamental disconnect. The executives speak the language of complexity in board meetings and congressional hearings, but the quants on the trading floor still use traditional models, just with more elaborate stress tests. James nodded thoughtfully. It reminds me of what's happening in climate science and environmental policy. The concepts of tipping points and nonlinear feedbacks have become central to the discourse. Terms like irreversible threshold and critical transition appear in IPCC reports. And yet the policies don't fully reflect that understanding. Elaine finished his thought. The precautionary principle says we should avoid potentially catastrophic outcomes, even if their probability is uncertain. But our political systems seem poorly equipped for that kind of thinking. They fell silent, contemplating the intersection of complex systems and human institutions. Outside, a gust of wind drove snow against the windows, creating swirling patterns before disappearing. Have you seen the new mixers they're using at MIT's chemical engineering department? James asked, changing the subject to something more concrete. They've designed them based on chaotic advection principles, stretching and folding fluids for more efficient mixing. Elaine's eyes lit up. Yes, beautiful application. My company actually invested in a microfluidic device startup using similar principles for diagnostic tests. The physics is elegant, using chaos to create order, essentially. That's where chaos theory has had its clearest successes, James observed. In specific engineering applications, niche technologies where the mathematics translates directly to physical systems. Though not always mainstream, Elaine added. For every success story like weather forecasting or mixing devices, there are dozens of applications that remain specialized or experimental. The secure communication prototypes using chaotic carriers, for instance. Brilliant idea that never quite became commercially viable. Their conversation was interrupted by the arrival of Elaine's personal assistant, a distinguished man in his 50s who had been with her for over a decade. Dr. Westover, you asked me to remind you about the board meeting materials for tomorrow. Thank you, Robert. I'll review them later tonight. After he left, James smiled. Speaking of chaos in practical contexts, how do you find the current management philosophies? It seems every business book these days advises executives to embrace chaos and thrive on uncertainty. Elaine laughed, a rich melodic sound that filled the room. Oh, don't get me started. The business world's adoption of chaos theory has been creative, to put it kindly. I attended a leadership conference last month, James added, where a consultant with no scientific background spent an hour explaining how the butterfly effect means middle managers should feel empowered to make decisions without approval. Convenient interpretation, Elaine said, amused. Though I suppose there's a kernel of truth buried in there somewhere. The problem is, the metaphors have become disconnected from the mathematics, James observed. Agility, adaptability, emergent strategy, these can be valuable business concepts, but they're only loosely related to actual chaos theory. Elaine nodded. The same thing has happened with activism and social movements. Be the butterfly. I saw that on protest signs during the climate marches. The idea that small actions can trigger system-wide change, which can be both empowering and misleading, James replied. On one hand, it gives people a sense of agency in the face of enormous challenges. On the other hand, it can oversimplify the mechanisms of social change. Slacktivism, Elaine suggested. The illusion that small symbolic actions will inevitably cascade into systemic transformation, without the hard work of building movements, forming coalitions, changing policies, James agreed. The butterfly effect becomes an excuse for vagueness about strategy. The snow continued to fall outside, transforming New York into a different city, quieter, softer, its harsh edges blurred. "What about your work in cardiac arrhythmias?" James asked after a moment. "Last time we spoke, you were optimistic about chaos control techniques." Elaine's expression grew more serious. "Progress has been slower than I'd hoped. The mathematical models suggest we should be able to use tiny perturbations to nudge an irregular heartbeat back into a stable pattern. But the human heart is more complex than a chaotic circuit or a dripping faucet." She walked to her bookshelf and pulled down a medical journal. This paper from last year shows some promise with real-time monitoring of heart rate variability as a diagnostic tool. Reduced complexity in the signal can indicate problems before conventional measures show anything alarming. But not yet at the intervention stage. "Not yet," Elaine admitted, "though I remain hopeful. The patterns are there. We can see them in the data. It's translating that understanding into reliable clinical applications that's proving challenging." James nodded sympathetically. "Science proceeds more slowly than our ambitions." "Indeed," Elaine agreed, "though I sometimes wonder if we've been looking in the wrong direction. Perhaps the most significant impact of chaos theory isn't in direct applications, but in how it's changed scientific practice itself." "The rise of computational experimentation," James suggested. "Exactly. When I was in medical school, experiments happened in laboratories with physical equipment. Now some of our most important work happens in silico. Simulations, visualizations, computational models." "A methodological revolution," James agreed. "Chaos theory helped drive that transformation, along with increased computing power." "And the visualization techniques," Elaine added. "Being able to see strange attractors, basins of attraction, phase space. It's changed how we think about systems, even when we're not explicitly using chaos mathematics." The evening continued, their conversation flowing from topic to topic. The latest developments in nonlinear science, the challenges of interdisciplinary research, the gaps between theoretical understanding and practical application. Later, as James prepared to leave, he paused at the door. "Do you ever wonder what Edward Lorenz would think of how his work has been applied, or misapplied, across so many domains?" Elaine smiled reflectively. "I imagine he'd be fascinated by the legitimate applications, the weather forecasting, the mixing devices, the control systems, and bemused by the metaphorical extensions into business and self-help. And perhaps a bit concerned about how some have oversold the implications." "Yes," she agreed. "Though that's the fate of any powerful idea, isn't it? To be stretched beyond its proper domain, to be both tool and metaphor." The snow had stopped, and Manhattan gleamed below them, its lights reflecting off fresh snow. James donned his coat and shook Elaine's hand. Until our next discussion, Doctor. Indeed, Professor. Safe travels. After he left, Elaine returned to the window, gazing at the city below. The patterns of streets and lights, the flow of traffic, the complex interactions of millions of lives. A system too complex to fully comprehend, yet not entirely unpredictable either. She smiled to herself, thinking of how far chaos theory had come from its mathematical origins to influence fields, from medicine to finance, from engineering to activism. The mathematics had proven more powerful and more limited than anyone could have foreseen, changing both how scientists worked and how many people understood the world. Tomorrow, she would return to her research, trying to bridge the gap between elegant theory and messy reality. But tonight, she was content to contemplate the strange attractor of human knowledge, always evolving, never repeating, yet somehow maintaining its shape across time. Morgan shifted uncomfortably in the plush leather seat, watching silver rain stream down the window of his penthouse office. Beyond the glass, Manhattan glittered like a circuit board in the gathering twilight. The projector hummed behind him, casting the famous Jurassic Park scene onto the wall. "Life finds a way," intoned Jeff Goldblum's character, the self-proclaimed chaotician Dr. Ian Malcolm. Morgan paused the frame with the remote and turned to his guest. "Fascinating, isn't it? The moment millions of moviegoers first encountered chaos theory in 1993. Elise Chen, the media studies professor he'd invited to consult on his investment firm's new predictive algorithms, merely raised an eyebrow. "It's certainly memorable." Goldblum in that black leather jacket, leaning back, explaining complex mathematics between flirtatious remarks. "You sound unimpressed," Morgan noted. "Not unimpressed," Elise corrected, crossing her legs. "Just aware of the simplification. Malcolm represents chaos theory as essentially a prophet of doom, predicting the park's inevitable collapse due to its complexity. He's correct within the film's narrative, but he's not doing what actual chaos theorists do, which is model, measure, test. Real chaos science isn't just saying complex systems eventually fail. It's about understanding the patterns within apparent randomness." Elise stood and walked to the rain-streaked window. "Malcolm is a prophet with equations, not a scientist. The film uses chaos as a metaphor for hubris, which makes for compelling storytelling, but incomplete science." Morgan followed her gaze toward the city lights blurring through the raindrops. Yet, that scene introduced millions to the concept, and simultaneously misled them, Elise said softly. "Pop culture has a way of doing that." 2 evenings later, they sat in Morgan's private screening room, the credits for The Butterfly Effect rolling across the screen. The 2004 film starred Ashton Kutcher as a young man who discovers he can rewrite his past, creating divergent timelines with each change. "Another fundamental misunderstanding," Elise sighed, reaching for her wine glass. "This isn't chaos theory at all. It's time travel fiction with a borrowed name." Morgan leaned forward. "Explain the difference." The butterfly effect, a term coined by meteorologist Edward Lorenz, simply states that small changes in initial conditions can lead to vastly different outcomes over time. But these outcomes unfold in a single timeline through deterministic equations. The red wine caught the light as she swirled it. The film conflates chaos with branching realities, retrocausation, and the multiverse concept. Chaos theory doesn't let you rewrite the past. Yet the film grossed over $96 million worldwide, Morgan mused. People love the idea that small actions have enormous consequences. It's narratively satisfying, morally resonant. But most audiences left thinking chaos theory is about parallel universes or fate. What about Ray Bradbury's A Sound of Thunder? Morgan asked. The 1952 story where a time traveler steps on a prehistoric butterfly and changes history. Elise smiled. Predates chaos theory's popularization by decades. Bradbury wasn't referencing Lorenz's work. He was exploring the fragility of history. Later, when chaos theory gained prominence, people retroactively connected the story to the butterfly effect. It's a case of cultural convergence. Rain continued to drum against the skylight above them, creating fractal patterns of shadow across their faces. The following morning, Morgan's private gallery had been transformed. His assistants had curated an exhibition of chaos theory in visual culture. Photographs, prints, and digital displays representing 30 years of artistic interpretation. The visual language of chaos has become ubiquitous, Elise said, gesturing toward a wall of images. Fractals in advertising. The Lorenz attractor appearing in corporate logos. Mandelbrot sets on album covers. They paused before a series of psychedelic art prints from the early 1990s. Swirling, self-similar patterns in neon colors. The rave culture particularly embraced fractal aesthetics, Elise continued. There's something about these infinite recursive patterns that resonates with altered states of consciousness. And here, Morgan pointed to a vintage computer monitor running an old screensaver. Microsoft's Mystify screensaver from Windows 95. Millions stared at these patterns daily, not knowing they were watching chaos mathematics visualized. Elise nodded. Then there's the Lorenz attractor itself, that butterfly-shaped diagram of a chaotic system's evolution. It's become an icon of complexity, appearing everywhere, from textbook covers to tattoos. They moved to a display of popular video games. Even gaming embraced the concept, Morgan observed. Games advertising emergent gameplay or procedural generation often invoke chaos theory in their marketing. Though most merely create complex but deterministic systems, Elise added, true mathematical chaos is rarely implemented. Morgan paused before a wall of book covers. Chaos by James Gleick, 1987. The book that popularized chaos theory for general audiences. And look how many novels borrowed the terminology afterward. It became literary shorthand for unpredictability, Elise said. Michael Crichton used it extensively, not just in Jurassic Park, but throughout his work. Tom Stoppard's play Arcadia wove chaos theory into discussions of thermodynamics and romantic relationships. And here, Morgan indicated a collection of music albums. Chaos theory, as a title, appears across genres. Electronic, metal, jazz, classical. It's evocative terminology, Elise acknowledged. It suggests complexity, depth, unpredictability, qualities artists aspire to. Rain shadows danced across the gallery floor as clouds shifted outside. That evening, they dined at Morgan's private table overlooking Central Park, city light shimmering through the persistent rain. What troubles me, Morgan said, cutting into his steak, is how pop culture consistently misrepresents the core concepts. The confusion of chaos with randomness. The implication that chaos means inevitable catastrophe rather than a specific mathematical behavior. People crave narratives about unpredictability, Elise replied. Look at films like Sliding Doors or Run Lola Run. They're not explicitly about chaos theory, but they play with the same idea of small changes leading to radically different outcomes. Then there's the conflation with quantum physics, Morgan added. The multiverse concept is more quantum mechanical than chaotic, yet popular media mixes them freely, Elise nodded. Hollywood science is collage science, pieces assembled for dramatic effect rather than accuracy. What about the trope of the eccentric genius who sees patterns others miss? Morgan asked. Malcolm in Jurassic Park, or John Nash in A Beautiful Mind, though that's game theory, not chaos. Media loves the pattern-recognizing savant, Elise agreed. It's visually compelling to show someone connecting invisible dots. But real chaos science is collaborative, incremental, and far less dramatic. Lightning flashed outside, briefly illuminating the rain into silver threads. What fascinates me most, Elise continued after a moment, is how chaos theory has become a metaphor for our relationship with uncertainty. In the 17th century, Laplace imagined a demon who could predict everything if it knew the position and momentum of every particle. Chaos theory told us that demon couldn't exist, not because of quantum uncertainty, but because even in a deterministic universe, perfect prediction is impossible. A troubling thought for someone in my line of work, Morgan said wryly. Investment banking relies on predictive models, yet your industry has adapted, hasn't it? Using ensemble forecasting, scenario analysis, tools developed partly in response to chaos theory. Morgan nodded slowly. We've learned to quantify uncertainty rather than eliminate it. Exactly what meteorologists did, Elise said. They couldn't predict a specific weather pattern weeks ahead, so they ran multiple simulations with slightly different starting conditions to generate probability distributions. Morgan refilled their wine glasses. Pop culture rarely captures that nuance. It prefers the dramatic butterfly causing a hurricane to the more accurate picture of probabilistic forecasting. Entertainment versus education, Elise said. The former will always simplify the latter. Outside, the rain intensified, drumming against the glass like countless tiny butterflies' wings. Later, they stood on Morgan's covered terrace, watching the storm over the city. Lightning occasionally illuminated the clouds from within, revealing turbulent, chaotic structures that formed and dissolved in seconds. There's one aspect of chaos in media we haven't discussed, Elise said. The use of chaos as political metaphor. Morgan raised an eyebrow. Go on. Consider how often chaos appears in headlines about market fluctuations, civil unrest, or political upheaval. It's rarely referring to mathematical chaos. It's invoking disorder, breakdown, entropy. Suggesting systems out of control, Morgan mused. Precisely. And that creates tension with the scientific meaning. True chaos is deterministic, governed by rules, but unpredictable in detail. Political chaos is portrayed as ruleless, anarchic. She paused. The conflation serves certain narratives about the need for control. Thunder rolled across the sky, a bass note beneath the percussion of rain. So where does that leave us? Morgan asked. If popular culture has so thoroughly misrepresented chaos theory, has it done more harm than good? Elise considered this. I think of it as translation with inevitable distortion. Pop culture introduced millions to ideas they'd never have encountered otherwise. Yes, the science was simplified, sometimes distorted. But the core insight that complex systems behave in ways that resist simple prediction, that message got through. She turned to face him. And perhaps that humility about prediction is the most important lesson anyway. Morgan nodded slowly, especially for those of us who build models of the future. They stood in silence, watching patterns form in the raindrops streaming down the glass barriers. Each droplet following deterministic physics, yet creating patterns no algorithm could precisely predict. "I wonder," Morgan said finally, "what chaos theory looks like online now, how YouTube, Reddit, and TikTok have transformed these concepts." "That," Elise smiled, "is an entirely different kind of butterfly effect." The storm continued unabated, mathematical chaos manifesting in the real world above them. Beautiful, powerful, and fundamentally beyond complete understanding. Yet following rules all the same. Antonia remembered the first time she'd stumbled upon 3 blue 1 brown while battling insomnia at her estate in Connecticut. The animation of the Lorentz attractor had appeared on her screen at 3 a.m., mesmerizing her with its butterfly-like pattern oscillating in 3-dimensional space. Grant Sanderson's soothing voice had explained how this strange mathematical object emerged from simple differential equations, yet produced behavior that could never be predicted long-term. Now, years later, she sat in her private library, the rain tapping gently against the floor-to-ceiling windows that looked out over Long Island Sound. The storm was intensifying, matching her mood as she scrolled through her tablet. "I've fallen down another rabbit hole," she whispered to herself, taking a sip of her Darjeeling. The library's walnut shelves held first editions of Poincaré and Lorentz, but increasingly, Antonia found herself drawn to the digital ecosystem that had sprouted around chaos theory. She had discovered a network of communities online, academics sharing papers on R-curve, enthusiasts posting fractal zooms, philosophers debating determinism on obscure forums. It was as if chaos theory existed in 2 parallel universes. The rigorous mathematical discipline documented in her leather-bound books, and this vibrant, messy digital culture that both illuminated and distorted it. Her screen currently displayed a Reddit thread in r/complex systems, where someone had asked about the relationship between chaos theory and quantum mechanics. The top comment began with, "These are completely different phenomena," before launching into a detailed explanation. But further down, upvoted nearly as highly, someone had confidently asserted that chaos theory proves quantum entanglement affects macroscopic systems, a claim that made Antonia wince. She switched to YouTube, where her recommendations had become increasingly dominated by chaos-related content. Numberphile's video on the Mandelbrot set had over 5 million views. Veritasium had produced a slick explanation of the double pendulum that had been watched almost 10 million times. The comment sections were filled with people expressing wonder, asking questions, making connections, some insightful, many misguided. "Democratized knowledge," Antonia murmured, "both blessing and curse." Thunder rolled outside as she remembered a conversation with Dr. Emerson, the mathematician she'd met at a Princeton gala last fall. They'd stood on the terrace, champagne in hand, discussing this very phenomenon. "These YouTube channels are doing what textbooks never could," Emerson had said, gesturing with his glass. 3 blue 1 brown visualizes concepts in ways that make intuition possible. "Students come to my office hours already understanding bifurcation diagrams, because they've seen them animated, manipulated them in simulations. But at what cost? Antonia had countered. The rigor gets lost. I saw someone on TikTok explaining the butterfly effect as everything affects everything, while fractal patterns swirled in the background. 60 seconds, 10 million views, and not a differential equation in sight. Emerson had smiled. The tension between accessibility and precision. The eternal struggle? Lightning flashed now, briefly illuminating the dark corners of her library. Antonia navigated to TikTok, where her private account followed several scientists and educators. She scrolled through an endless stream of short videos. Fractals set to electronic music, butterfly emojis followed by tornado emojis, captions declaring when small changes have massive effects, over clips of dominoes falling. One creator, a physics graduate student with 3 million followers, had condensed Lyapunov exponents into a 20-second explanation that was surprisingly accurate, if necessarily incomplete. Another showed the bifurcation diagram for the logistic map being revealed slowly, the road to chaos, while dramatic music played. Antonia found herself conflicted. On one hand, she recognized that these platforms were bringing complex mathematics to audiences who would never encounter it otherwise. On the other hand, something was lost in translation. The precision, the limitations, the careful statements of what was known versus what was conjectured. She navigated to ResearchGate, where her status as a philanthropic funder of mathematics research gave her access to papers behind academic paywalls. Here was the other end of the spectrum: dense mathematical notation, careful peer review, incremental advances on well-defined problems. A recent paper examined basin boundary fractals in a specific family of dynamical systems. Work that would never go viral, but represented genuine progress in understanding. Between these extremes, viral content and specialist papers, lay communities like Stack Exchange and the Chaos Theory subreddit, where enthusiasts and professionals interacted directly. Questions ranged from undergraduate homework problems to speculative applications in finance. Some received detailed, thoughtful responses. Others spiraled into misunderstandings or debates. Antonia switched back to YouTube and searched for Chaos Theory Explained. The results were telling. The most viewed videos had thumbnails featuring butterflies, storms, and fractals. Titles promised to reveal why we can't predict the future, or how tiny changes create massive effects. The actual mathematics appeared only in the more specialized channels, with smaller audiences. The spectacle outperforms the substance, she said to herself. Her phone chimed with a notification, an email from the Santa Fe Institute, where she served on the board. They were planning a workshop on communicating complex systems science to the public, addressing exactly this tension between accuracy and engagement. The Institute had been experimenting with interactive notebooks, where people could manipulate equations and see results in real time, trying to find a middle ground between passive consumption and mathematical rigor. As she composed her reply, Antonia reflected on her own journey with chaos theory. She had first encountered it, not through formal education, but through James Gleick's book, itself a bridge between technical understanding and popular accessibility. Later, she had hired tutors, attended seminars, eventually funded a chair in nonlinear dynamics at MIT. The internet had accelerated and transformed this learning process, making primary sources instantly available while simultaneously drowning them in noise. The rain intensified, droplets streaming down the windows in chaotic rivulets that never followed the same path twice. Antonia opened Twitter, where her timeline showed someone had shared an image of the Lorentz attractor with the caption, "When you realize your life was determined but unpredictable, all," along hashtag chaos theory. The post had thousands of likes and hundreds of comments. Some made jokes about sensitive dependence on initial conditions, explaining their poor life choices. Others debated free will versus determinism. A few pointed out that chaos theory didn't actually say anything about human psychology or decision-making. Scrolling further, she found a widely shared quote attributed to Edward Lorenz. "Chaos. When the present determines the future, but the approximate present does not approximately determine the future." The quote was legitimate, one of the few that hadn't been mangled or fabricated in the meme ecosystem. But below it, someone had added, "Quantum physics proves we create our own reality through observation. Chaos theory shows how." This conflation of distinct scientific domains, a common pattern online, had received hundreds of endorsements. Antonia set down her tablet with a sigh. The internet's handling of chaos theory reflected the theory itself. Initial conditions, the actual mathematics, led to unpredictable outcomes, interpretations and applications, through nonlinear processes, social media algorithms, human psychology, economic incentives. She rose and walked to the windows, watching lightning illuminate the choppy waters of the Sound. The weather system outside was itself a chaotic process, predictable in the short term through ensemble forecasting, fundamentally unpredictable beyond a horizon of about 2 weeks. Yet here it was, not just as an abstract concept, but as lived reality. Perhaps this was why chaos theory resonated so deeply in digital culture. It spoke to a fundamental truth about our relationship with the world. That perfect prediction was impossible. That small influences could cascade into large effects. That patterns could emerge from seeming randomness. These insights had mathematical formulations, yes, but they also spoke to human experience in ways that transcended equations. The challenge was preserving the precision while acknowledging the poetry. Antonia returned to her desk and opened her laptop. She had been drafting an email to the organizers of a conference on science communication, suggesting a panel on chaos theory in digital culture. Now, with renewed purpose, she completed it. The internet has transformed chaos theory from an academic specialty into a cultural touchstone. This transition offers unprecedented opportunities for education while creating new challenges for scientific integrity. I propose bringing together YouTube educators, Reddit moderators, research mathematicians, and science journalists to discuss how we might cultivate digital spaces where rigor and accessibility coexist, where the butterfly and the differential equation both have their place. She sent the email, then returned to her tablet. One last search. Chaos theory, interactive simulation. Among the results was a new project from 3 Blue 1 Brown, an open-source tool that allowed users to explore dynamical systems by adjusting parameters and watching the resulting behavior, complete with visualizations of phase space and explanations of the underlying mathematics. The comments section was filled with people sharing discoveries, asking questions, helping each other understand. Here, perhaps, was a glimpse of what was possible. Technology enabling not just passive consumption of simplified explanations, but active exploration of complex ideas. Outside, the storm began to subside. Antonia closed her eyes and listened to the diminishing rainfall, aware that tomorrow's weather forecast, produced by supercomputers running ensemble simulations of atmospheric physics, would be remarkably accurate for the next few days, then increasingly uncertain beyond that. This balance between what we can know and what we cannot, between determinism and unpredictability, was the essence of chaos theory. And in the digital age, that balance was being renegotiated in comment sections and subreddits, in viral videos and interactive simulations, in memes and academic papers. The challenge was not to eliminate simplification, that was both inevitable and necessary, but to ensure it led toward rather than away from deeper understanding. To create digital ecosystems where fascination with the butterfly effect might eventually lead to appreciation of Lyapunov exponents, where the visually stunning fractal zoom might eventually prompt curiosity about the mathematics that generated it. As darkness fell outside her windows, Antonia returned to her reading chair. Tomorrow she would call the Santa Fe Institute about funding their interactive learning tools. For tonight, she opened her tablet one more time and typed 3 blue 1 brown chaos theory into the search bar. Perhaps it's time to revisit where her own digital journey had begun, to experience again that rare moment when rigorous mathematics became not just comprehensible, but beautiful. The soft glow of the screens in Jonathan's private study cast azure shadows across the mahogany walls. Outside, rain pattered against bulletproof glass. The Manhattan skyline transformed into a watercolor of smudged lights. The billionaire hedge fund manager sipped his 40-year-old Balvenie, feeling the familiar burn as he scrolled through the final report prepared by his team of chaos theorists. "This is what certainty costs," he murmured, tracing a finger over the screen. 5 years ago, Jonathan had diverted $200 million of his personal fortune into what his board called the epistemological vanity project. Now, as the thunder rolled across the sky, he reviewed the summary that might finally separate truth from fantasy in the realm of chaos theory. The report began with the well-grounded claims, the bedrock of certainty, purchased through decades of meticulous research. "Mathematical chaos isn't speculation, it's fact," he read, voice barely audible above the rain. "The logistic map, Lorentz equations, double pendulum. These aren't merely models, they're demonstrations of a profound truth. Deterministic systems can behave unpredictably." Jonathan paused at a visualization of the Lorentz attractor, its butterfly-like wings rendered in impossible detail. The mathematics behind it had been proven rigorously. Sensitivity to initial conditions was real. In these systems, small errors grew exponentially over time, not as metaphor, but as mathematical certainty. He scrolled to a section on strange attractors, admiring their fractal structure, infinite detail at every scale, self-similarity that bordered on the mystical while remaining entirely within the realm of mathematics. This, too, was certain. "And weather," he whispered, glancing at the storm outside. 10 to 14 days. That's our limit." The report confirmed what meteorologists had known for decades. Beyond 2 weeks, weather forecasting became fundamentally impossible. Not because of technological limitations, but because of intrinsic chaos. Jonathan had once lost $80 million betting against this principle. He wouldn't make that mistake again. His finger hesitated over the next section, moderately grounded claims. Here, certainty began to blur at the edges. like the city lights outside his window. Plausible, with caveats, he read. The report detailed biological systems where chaos seemed present. Heart rhythms, neural firing patterns, predator-prey cycles. The evidence was suggestive, compelling even, but not definitive. In controlled laboratory settings, certain biological processes displayed hallmarks of chaos, but proving low-dimensional deterministic chaos in the wild remained challenging. Like hunting ghosts, Jonathan muttered. He thought of his late wife's heart condition. The loss of complexity hypothesis had fascinated him. The idea that healthy hearts displayed chaotic variability, while failing hearts became too regular. Her doctors had shown him the heart rate variability plots, explaining that decreasing complexity often preceded cardiac events. He'd funded 3 research labs investigating this phenomenon after her passing. The evidence was strong enough to guide clinical decisions, yet the underlying theory remained contested. Was it truly chaos in the mathematical sense, or something else entirely? Jonathan refilled his glass and moved to engineering applications. Chaos control techniques worked reliably in mixers, lasers, certain circuit designs, but they weren't universal solutions. Another well-supported but limited claim. Then came the section that had consumed billions in misguided investments. Speculative or weakly supported claims. These are oversold. Jonathan read aloud, his voice tinged with the bitterness of experience. Financial markets topped the list. Despite decades of searching, the evidence for low-dimensional, deterministic chaos in market behavior remained weak. Markets behaved more like high-dimensional stochastic systems, randomness with structure, but not the elegant mathematics of the Lorenz attractor. Jonathan had once believed otherwise. In the early 2000s, he'd assembled a team of physicists and mathematicians to hunt for strange attractors in market data. Their algorithms sought patterns that could distinguish chaos from noise, reconstructing phase spaces from price movements, calculating Lyapunov exponents and correlation dimensions. They'd found something. Patterns that seemed significant, forecasts that occasionally outperformed random chance. For 3 glorious months, the strategy yielded returns that defied conventional models. Then it collapsed, catastrophically. In retrospect, the explanation was painfully obvious. They'd been fooled by noise. High-dimensional randomness could masquerade as low-dimensional chaos when analyzed with finite noisy data. The patterns they discovered were statistical mirages, ephemeral structures in the randomness that their algorithms had mistaken for deterministic chaos. A $200 million lesson in epistemic humility, Jonathan muttered, scrolling further. The report continued with even more tenuous claims. Chaos theory proving or refuting free will. A philosophical leap, not a mathematical conclusion. Claims that Eastern mysticism had somehow anticipated chaos theory. Poetic resonance, perhaps, but not scientific validation. And then there was the butterfly effect, as applied to human affairs. The notion that tiny actions inevitably cascade into world-changing consequences. Jonathan had once found this idea profoundly moving, even building his charitable foundation around it. Small interventions, massive impacts had been their tagline. But the report was unequivocal. While sensitivity to initial conditions was mathematically sound, its literal application to social systems remained metaphorical, not quantitative. Some small actions might have large consequences, others none at all. The butterfly in Brazil might indeed influence a tornado in Texas, or it might not. Prediction was the issue, not possibility. The final section addressed methodological uncertainties. Even with modern computing power, distinguishing low-dimensional chaos from high-dimensional noise remained challenging. Measuring fractal dimensions reliably in real-world data presented formidable obstacles. Time series analysis tools had fundamental limitations when applied to systems with many variables or significant noise. Outside, lightning split the sky, illuminating the room in stark white for a moment. In that flash, Jonathan caught sight of his reflection in the window, older than he remembered, more tired. He closed the report and walked to the rain-streaked glass, 68 floors above the city. From this height, patterns emerged that weren't visible at street level. The flow of traffic, the organization of buildings, the human currents moving through concrete channels. The chaos theory report had cost him millions, but its value couldn't be calculated in currency. It had given him something more precious, a map of certainty. It showed him which claims to trust, which to question, and which to discard entirely. Jonathan pressed his palm against the cool glass. Chaos theory was both smaller and larger than its popular reputation suggested. Smaller in scope. It didn't explain everything from weather to war, markets to marriages. Larger in implication, it fundamentally reshaped how we understand knowledge, control, and the future. "Sir," came the voice of his assistant through the intercom. "Your helicopter is ready whenever you wish to depart." Jonathan glanced at his watch. The storm was intensifying, but the report included weather forecasts using ensemble methods, another triumph of chaos theory. Multiple simulations with slightly different initial conditions, revealing the range of possible outcomes rather than a single prediction. The storm would peak in 30 minutes, then offer a 2-hour window of calmer conditions before the next system arrived. "Prepare for departure in 40 minutes, he instructed. He returned to his desk and transferred the report to his secure archive. Tomorrow, he would begin redistributing research funds based on its conclusions, more for heart rhythm analysis, less for market prediction algorithms. The Foundation would revise its messaging, replacing butterfly effect rhetoric with more nuanced language about complex systems. As he closed the system, Jonathan felt an unfamiliar emotion, not the exhilaration of discovery or the satisfaction of control, but something quieter. Perhaps it was the peace that comes with knowing the boundaries of knowledge, understanding what we know, what we partially know, and what remains beyond our grasp. Outside, the rain continued its chaotic pattern, each drop determined yet unpredictable, part of a system too complex to fully comprehend, yet governed by principles we could partially discern. Jonathan stood at the window a moment longer, watching the interplay of light and water, finding in it a perfect metaphor for what his expensive report had taught him. "Not everything is chaos," he whispered to the storm, "but chaos is everywhere, if you know how to look." The night had deepened outside my study window, stars flickering through the occasional gap in the cloud cover. The soft glow of my desk lamp illuminated the scattered papers, printouts of the Lorentz attractor, its butterfly-like loops now familiar after our journey through chaos theory. I ran my fingers over the curves, feeling the texture of the paper, contemplating the strange beauty of this mathematical object that had revolutionized our understanding of the world. Picture the Lorentz attractor one more time. Two looping spirals, never repeating, never intersecting, infinitely complex, yet contained within a finite space. It's deterministic. Every point follows Newton's laws precisely, but it's unpredictable. You cannot forecast where the trajectory will be after 100 iterations, no matter how precisely you measure its starting position. I leaned back in my leather chair, the material creaking slightly as I shifted. This was the paradox at the heart of chaos. A universe ruled by immutable laws that nonetheless surprises us at every turn. Order and disorder aren't opposites. They coexist, intertwined within the same equations. The realization felt like standing at the edge of a precipice, terrifying yet exhilarating. The rain began to patter against the window pane, each droplet following a chaotic path down the glass. I watched them merge and separate, thinking about how these simple phenomena contained such profound complexity. The soft rhythm of the rainfall provided a soundtrack to my contemplation of the vast implications of what we'd explored. Chaos theory represents one of the most significant paradigm shifts in scientific thinking since quantum mechanics. It fundamentally altered our concept of determinism, showing that perfect predictability wasn't just practically difficult but theoretically impossible in many systems. From Lorentz's isolated strange attractors, science has expanded into a broader complexity paradigm, embracing emergent phenomena, network theory, and self-organization. This isn't just a mathematical curiosity. It's a framework for understanding everything from financial markets to ecosystems to the human brain. I walked to the window, watching lightning flash in the distance. 23 seconds later, thunder rolled across the valley. Weather. The original chaotic system that had inspired Lorentz's discovery. We can predict tomorrow's weather with reasonable accuracy, next week's with considerable uncertainty, and next month's hardly at all. Not because our instruments are inadequate or our computers too slow, but because the system itself resists long-term prediction. This realization should humble us. I pressed my forehead against the cool glass, watching my breath create a small circle of fog. So much of our world operates this way, determined but unpredictable. The stock market follows iron laws of supply and demand, yet defies precise forecasting. Traffic patterns emerge from simple rules but resist control. Even our bodies, those intricate networks of chemical reactions, contain chaotic subsystems that can amplify tiny fluctuations into significant outcomes. But we must be careful where we apply this insight. Chaos is a precise technical tool in some domains, not a loose metaphor to be carelessly extended to others. In weather forecasting, fluid dynamics, and certain mechanical systems, chaos theory provides rigorous mathematical descriptions. But in psychology, economics, and social systems, the application becomes more tenuous. Not everything unpredictable is necessarily chaotic in the technical sense. I returned to my desk and opened a drawer, retrieving a small double pendulum I keep as a reminder of chaos in action. I set it in motion with a gentle push. The first few swings followed a predictable arc, but within seconds the pendulum began tracing wild, seemingly random patterns. Yet there was nothing random about it, just the deterministic amplification of imperceptible variations in my initial push. This humility about prediction isn't surrender to mysticism or an excuse for intellectual laziness. Rather, it's scientifically justified recognition of intrinsic limits. In truly chaotic systems, Uncertainty isn't something we can eliminate with better tools or more data. It's fundamental to the system's behavior. Acknowledging this limitation doesn't diminish science. It represents scientific progress, a more sophisticated understanding of reality's texture. The pendulum gradually slowed, its erratic swinging subsiding until it hung motionless once again. I wondered about the implications for human affairs. How many of our cherished certainties are illusory? How many of our confident predictions are fundamentally misguided? Politicians promise precise economic outcomes. Financial advisors forecast market returns. Futurists depict detailed visions of coming decades. Chaos theory suggests a more nuanced approach, acknowledging that some systems permit short-term forecasting while accepting the inherent unpredictability of long-term outcomes. For those intrigued by these ideas, many paths of exploration remain open. Advanced study in dynamical systems, nonlinear analysis, and complexity science offers rigorous mathematical foundations. The literature is rich, from Lorenz's accessible Essence of Chaos to Strogatz's more technical nonlinear dynamics and chaos. Computer simulations allow hands-on exploration. Watching simple rules generate astonishing complexity. But equally important is developing a critical eye toward pop chaos narratives. The concept has been stretched and distorted in media, self-help books, and policy rhetoric. Claims about chaos should be met with probing questions. Is this truly a deterministic system, showing sensitivity to initial conditions? Or is the term being used loosely to describe any unpredictable phenomenon? Is there empirical evidence for chaotic dynamics, or merely metaphorical application? The rain intensified outside, drumming against the roof. I thought about how chaos theory connects to other frontier fields: artificial intelligence, network science, climate modeling, and systems biology. The intersections are fertile ground for innovation. AI researchers grapple with chaotic dynamics in reinforcement learning. Climate scientists use ensemble forecasting to manage chaos in atmospheric models. Biologists explore chaotic patterns in neural firing and genetic regulation. These interdisciplinary connections represent the future. Chaos not as an isolated concept, but as one thread in the tapestry of complexity science. I closed my notebook and dimmed my desk lamp, leaving just enough light to observe the shadow of raindrops tracing unpredictable paths on my wall. In the half-light, I contemplated the central question that had accompanied us throughout. Can we predict the future? The answer is nuanced. Tomorrow's sunrise? Yes, with certainty. Next month's weather patterns? Roughly, with decreasing accuracy over time. Next year's stock prices? No. The path your life would have taken had you made one different choice 10 years ago. Almost certainly not. Chaos theory doesn't resolve ancient questions about free will versus determinism. It doesn't tell us the meaning of life or whether the universe has purpose. But it does reveal something profound. Reality is stranger than we imagined. The universe obeys mathematical laws we can write down, yet refuses to let us see what's coming. And perhaps that's not a failure of science, but a feature of existence itself. I stood by the window again, watching the storm clouds shift and reshape themselves. There was comfort in this uncertainty, a kind of freedom. If the future isn't written, not even in principle, then perhaps each moment contains genuine possibility. Our choices matter, even if their consequences exceed our ability to calculate them. The rain had stopped, and the clouds were beginning to part, revealing a star-filled sky. I thought about Edward Lorenz, sitting at his primitive computer in 1961, watching unexpected patterns emerge from his weather simulation. That moment of surprise, when his deterministic equations produced unpredictable results, opened a door to a new understanding of nature. It showed us order within chaos, chaos within order, and the limits of what we can ever truly know. I turned away from the window, the Lorenz attractor still visible on my desk. Its butterfly loops seemed to pulse with possibility in the dim light, a mathematical object that had changed how we see the world, not by offering certainty, but by teaching us to embrace complexity, to find wonder in a universe that follows rules, yet remains forever unpredictable. Epilogue. Return to the light. Reflection on the journey. We have traveled together through the currents of the universe, from the uncomputable depths of physical chaos to the subtle ripples of time and memory, and the sacred interplay of unpredictability and order. Every star, every thought, every choice has been a thread in the vast tapestry we have traced. Science revealed the patterns and limits of understanding. Philosophy illuminated the meaning behind the unfolding. And spirituality, art, and myth showed the sacred potential within the unknown. To reflect is to see the unity across perspectives, to recognize that knowledge is never singular, but arises from the dialogue between observation, intuition, and reverence. We arrive at this moment, poised between what we have seen and what we have yet to become, aware that the journey itself is the revelation, and that every question asked echoes across the infinite. The unity of chaos and order. Chaos and order are not enemies. They are two sides of the same cosmic coin. One provides the energy of unpredictability, the potential for creation. The other channels that energy, giving structure, rhythm, and continuity. Throughout the universe, from stellar nurseries to neural networks, we witness this delicate balance. Disorder gives rise to novelty, unpredictability sparks insight, and structure frames potential into perceivable meaning. In every heartbeat, every cycle, every thought, we find the dynamic tension between unpredictability and harmony. The sacred emerges not from pure order, nor from pure chaos, but from their constant interplay, a living equilibrium that guides evolution, consciousness, and life itself. To see this unity is to embrace the dance of existence, to recognize that the universe is neither random nor fixed, but a continuous, emergent symphony of possibility. Human responsibility. With understanding comes responsibility. We are not mere spectators of this unfolding reality. Our consciousness participates in the shaping of the universe. Our choices resonate far beyond the immediate. Every thought, every action, every intention sends ripples through the web of existence, altering patterns of connection, consequence, and meaning. Recognizing this power is both humbling and empowering. It is a reminder that human life is a sacred opportunity to act with awareness, to cultivate wisdom, and to honor the balance of chaos and order. We are stewards of possibility, guardians of the fragile threads that connect past, present, and future, and participants in the eternal dance of creation. To live consciously is to embrace responsibility without fear, to navigate the currents of time with insight and ethical intention. Memory, time, and perception. Time is not merely a measure of passing moments. It is a medium through which consciousness perceives, interprets, and shapes reality. Memory anchors us, connecting what has been to what is. Anticipation stretches forward, painting potential futures in the mind's eye. And perception integrates both, constructing the reality we navigate and inhabit. Every recollection, every imagined possibility, every conscious observation participates in the ongoing creation of the present. To understand memory and perception is to understand our place in the river of time. We are not carried helplessly along. We are co-creators, weaving the past, present, and future into a living, coherent tapestry. The light of awareness illuminates this flow, revealing the infinite dance of cause, effect, and potential. Stories, the sacredness of chaos. Revisited. Chaos is not absence, it is the source of potential, creativity, and transformation. From the swirling galaxies to the beating of the human heart, from sudden insight to societal shifts, chaos underpins the emergence of order and meaning. Religious and spiritual traditions have long honored this principle, seeing the unpredictable not as threat alone, but as the fertile ground where creation, insight, and divine revelation emerge. Embracing chaos is to honor the unknown, to recognize the sacred in unpredictability, and to participate consciously in the unfolding of life. It is a force that challenges, inspires, and ultimately elevates consciousness, reminding us that the divine is found not only in certainty, but in the dance between light and shadow, order and disorder. Stories, cosmic connection, and transcendence. We are not isolated observers. We are part of an infinite, interconnected web of existence. Every thought, action, and perception resonates across networks of life, consciousness, and matter. Through awareness, humans can glimpse this cosmic connection. We see that personal experience is intertwined with collective destiny, that individual consciousness is a reflection of universal consciousness. Transcendence is found in recognizing unity without losing individuality, in perceiving the dance of chaos and order across scales, and in honoring the profound mystery that binds all things. To live consciously is to merge insight with reverence, to experience the universe not as separate from ourselves, but as a luminous continuum in which we are participants, creators, and witnesses. Stories, the invitation to live consciously. Life is not a passive journey. We are called to participate consciously, to move with awareness, intention, and reverence. Each choice, each thought, each gesture sends ripples through the networks of existence, shaping reality in ways seen and unseen. To embrace this is to honor both chaos and order, to recognize uncertainty as an opportunity, and to cultivate presence as a form of creation. Conscious living transforms existence into a sacred act where every step is an engagement with the infinite, every breath a contribution to the evolving tapestry of reality. We are co-creators, empowered to illuminate the world through awareness, compassion, and imagination. Return to the light. The journey comes full circle. From the uncomputable chaos of the universe to the subtle currents of time, memory, and perception, and through the sacred dance of unpredictability and order, we arrive at this moment of illumination. We are witnesses, participants, and co-creators. Every action, every thought, every spark of consciousness ripples through the infinite tapestry of existence. Subscribe to the Hidden Framework. Turn on notifications. Like the videos. Step into awareness. Trace your ripples. Merge perception, memory, and intention. Let each choice resonate with the sacred rhythm of the cosmos, transforming uncertainty into insight and chaos into illumination and meaning. The light is not elsewhere. It flows within, through every observation, every action, every moment of mindful presence. Return to it, embrace it, and let it guide the unfolding story of life. This concludes the series, The Hidden Framework. The universe is alive, and so are you.